And eventually those pieces formed into what we know as asteroids and comets today.
While asteroids are leftover debris residing mostly between Mars and Jupiter, the vast majority of comets are to be found far beyond the orbit of Pluto. A region called the Kuiper Belt is believed to contain millions of them. And far more distant, surrounding the entire solar system, is a celestial sphere, the Oort cloud. Here, trillions of comets may reside. It's from these distant places that some comets find their way into our planetary neighborhood.
We now know that there's a sort of a cloud of icy, rocky bodies out there that are called long-period comets, or Oort cloud comets. These objects probably are remnants of the original gas cloud from which our solar system collapsed about 4.5 billion years ago. And they're still out there. Occasionally they make their way into the inner part of the solar system, and they can come in, and then we see them as comets.
Compared to asteroids with their dark surfaces, comets are show-offs. For as a comet approaches the sun, dusty ices on its surface heat and light up, turning into a cloud of gas and dust, often having a trailing tail that can be millions of miles long. To the ancients, comets were viewed as harbingers of impending doom. But today, dread has been replaced by fascination. For these interlopers are relics, made up of the oldest and most pristine matter in our solar system. And it seems likely that we have to thank them for having brought to Earth long ago the elements that have allowed life to develop on our planet.
We know for certain that a pretty large asteroid or comet is responsible for the extinction of the dinosaurs. So from that standpoint, they can be incredibly destructive. Of course, we wouldn't be here without that. Maybe we'd be walking lizard people, I don't know. But it's certainly true that life today is very much a product of an asteroid impact, a destructive one. On the flip side, we think that there's a very powerful role that these objects have played in the potential for building life on this planet and perhaps elsewhere. If we just start from the very beginning, which is the seed of an asteroid or comet, that tiny grain becomes a site where molecules can meet and form more complicated molecules. So they become nucleation sites for chemistry to occur. So you can start with simpler things, even like 2 hydrogen atoms, but eventually those build longer and longer chains of molecules, some of which can be very complex. And eventually, all of those complex chemicals can migrate to a planet. So we think that there's a role that comets and asteroids have played over billions of years in seeding our planet with some of the chemistry that it may have needed to eventually evolve life.
The best known of all comets is Halley. It revisits the Earth about every 76 years. Its 1986 appearance was a highly anticipated event. This was the first time, given the dawn of the space age, that it was possible to venture out and meet Halley. And no one was more excited about that possibility than the then new director of NASA's Jet Propulsion Laboratory, Bruce Murray. Murray was intent on reinvigorating JPL, which he believed was becoming too cautious with missions he dismissed as being gray mice. He wanted, instead, for the lab to create daring new technologies used to explore destinations that would excite the public. These kinds of missions he labeled purple pigeons, for it would be impossible to ignore them. And for Murray, a mission to comet Halley, a once-in-a-lifetime event, was made to order. But any spacecraft sent out to meet Halley would have to overcome a major challenge.
Comets in general are in crazy orbits. Some are retrograde, some are highly inclined, so they are not easy targets to get to, especially if you want to get to them and pass them fairly slowly so that you can study them in detail. Halley's comet in particular was in a tough orbit to get to, and so there were various proposals on how to get into the right orbit.
Halley's retrograde orbit means that it circles the Sun in the opposite direction of Earth's orbit. A spacecraft flying by Halley would be like two cars speeding past one another, offering little time for exploration. Any attempt to rendezvous and fly alongside Halley posed even greater challenges. But a radically new idea surfaced, designing a spacecraft to be propelled by the pressure of sunlight, solar photons, similar to how wind pushes a sailboat.
So you need an enormous amount of energy to slow down when you get there, stop. You need a huge amount of fuel. And the idea of the solar sail is that you would need the fuel because you could use changing solar pressure on the sail to handle your acceleration and deceleration. That's what made it such a really interesting, fascinating, and also problematic technology because it's not something anyone had ever done before. It was really a science fiction idea. It was kind of way out there, and lots of other JPL people thought it was nuts.
Two different concepts were put forth to capture the power of the sun. The most audacious of the two was called a heliogyro, a structure resembling a dozen helicopter blades stacked atop one another, each 4 miles in length. They were to use the sun to spin up to 200 times a second. In comparison, the solar sail seemed almost conservative. Astronauts were to deploy from the space shuttle a razor-thin sail stretching a half-mile in length on all sides. Murray was so taken with the solar sail that he enlisted colleagues, including his friend, the popular scientist Carl Sagan, to help drum up support for a Halley mission. It was an effort that reached from the halls of Congress to Hollywood.
Now, what would this do?
Well, it takes you to where you want to go. So one mission that's being talked about is to rendezvous with Halley's Comet.
I've always wanted to do that.
Well, nobody's ever looked at a comet close up, and it lives mostly in the outermost part of the solar system. In fact, mostly lives between the stars. It's a piece of interstellar matter, and it'd be just fabulous to find out what it is. Also, this thing itself is, I think, tremendously exciting because, first of all, as it would be assembled in Earth orbit, it would be bright enough to see with the naked eye. Through a pair of binoculars, you could...
Solar sails and heliogyros were ideas far ahead of their time. But there was another purple pigeon whose development was further along. Solar electric propulsion, also known as ion propulsion.
Dr. Kenneth Atkins of the Jet Propulsion Laboratory described the advanced propulsion system.
Ion propulsion capability is 10 times as efficient as our conventional chemical rockets. And I think this is what gives us the capability to achieve a comet rendezvous.
When ion propulsion, like the solar sail, failed to gain traction, Murray next advocated a sample return mission, flying through the tail of Halley to capture some of its dust and bring it back to Earth to be retrieved by astronauts. It was another purple pigeon that never got off the ground, despite pleas from scientists.
For the first time in history, our children might be able to tell their children that they are the citizens of a nation which, for the first time, didn't simply and helplessly watch Halley fly by, but actually went out to meet it and to explore it.
In the end, it was the Soviet Union, Japan, and Europe that went forward with missions to meet the comet, what came to be known as Halley's Armada, a space fleet having no American presence, but one guided by two newly arrived scientists at JPL who were experts in tracking celestial bodies.
Our real role in the Comet Halley missions was, one, we had to predict where the comet was. That was my job. For the Soviets, for the Europeans, for the Japanese. And then we ran the International Halley Watch, which was a ground-based program to observe the comet in the infrared and the visible region to get astrometric data of where the comet was at any particular time.
Halley's Comet was kind of a training ground for myself, at least, for generating and writing software that could calculate some of the interesting questions that were being asked. In particular, questions like, how close is Halley's Comet coming to the Earth, and things like that.
In a face-saving gesture, NASA repurposed and gave a new name to a spacecraft near the end of its life and flew it past a comet. But there was no camera aboard, and it wasn't Halley's comet. Eventually, Halley receded from view, as did Bruce Murray. Frustrated by what he believed was a U.S. retreat from exploring the solar system, he stepped down as JPL's director 4 years before Halley's arrival.
Murray burned a lot of bridges with his campaigns for the Purple Pigeons and otherwise to save JPL. And at the time, well, then as now, NASA headquarters doesn't like it when centers kind of go off on their own to try to promote what they want to do and not what NASA headquarters has agreed with the White House should be done.
While none of Murray's Purple Pigeons took flight during his tenure, many of them would in years that followed. And looking back, perhaps what was more important for JPL than sending a spacecraft to Halley was the lab's pioneering work in predicting the path of the comet. For that accomplishment laid the foundation for JPL's future world leadership role in tracking near-Earth objects that could pose a threat to our planet and everything on it. Seven years after Halley's visit, 3 astronomers atop Palomar Mountain in California were searching the night sky for comets.
Could you please introduce yourself and tell me what you're doing there?
Yes, I'm Carolyn Shoemaker with a stereo microscope that was built specially to look at our films.
Okay, Mr. Shoemaker. What are we doing and what's going on tonight?
Well, what I'm doing here is laying out our game plan for tonight. We'll probably take about 50 films tonight.
Their luck had not been good. For months, they had experienced bad weather and cloudy skies.
It was snowing. It was just about the lowest point of all of our years at Palomar. 3rd straight month with virtually no observing.
During what seemed sure to be another disappointing night, the clouds briefly parted, and they rushed to the telescope and captured a puzzling image. It was an object near Jupiter, but it looked nothing like a comet. Was it, they wondered, just a reflection of Jupiter? Or perhaps some galaxy seen edge-on? It turned out that the astronomers, Eugene and Carolyn Shoemaker and David Levy, had discovered a comet, and one like nothing ever seen before. Named after the 3 astronomers, Shoemaker-Levy 9 turned out to be a comet that 8 months before its discovery had broken into pieces due to Jupiter's gravitational influence.
And over the ensuing month, we learned that not only was this comet orbiting Jupiter, very unusual for a comet, but that it would impact Jupiter. And it wasn't just one impact, it was 21 impacts because the comet had broken up into the string of pearls. And so, a real challenge, by the way, to calculate individual orbits for all those fragments. And I could confirm that with this software I had only recently developed. That was really the first real exercise of an impact probability calculation. It was for Jupiter.
This is a totally new event. It's the first time in the history of civilization, the history of the telescope, we are seeing an impact of a comet into a planet. Because of this, we are mounting the largest single campaign, the largest observing campaign for a single event in the history of astronomy. The good news is that it's going to do a spectacular demise into the atmosphere of Jupiter. The bad news is it's going to do it on the wrong side of Jupiter.
What Levy meant by the wrong side of Jupiter was that the fragments, which were estimated to range as much as a mile across, would be crashing into the backside of Jupiter as seen from Earth. And that meant that no telescope on Earth would be able to witness the actual impacts as they occurred. But on its way to Jupiter was JPL's Galileo spacecraft. By mere happenstance, Galileo would be in a position to witness the impacts live.
The Galileo spacecraft was en route to Jupiter and that could look at the impact zone directly, whereas from Earth, all the impacts occurred on the backside and they rotated into view.
About an hour after each impact, the crash sites would be viewable from Earth, allowing ground telescopes to witness the aftermath. The excitement in the astronomy community about such an extraordinary event quickly began generating extra sensational press.
However, I was at the supermarket last Thursday, in the line, and I picked up a copy of The Sun. It's one of these tabloids that you slip underneath your six-pack of Coke on the way out. And anyway, it says, comet crash will start U.S. ice age. No government agency will verify the impending day of doom, but sources say that's only because they want to prevent wide-scale panic and rioting. This is a report by Mr. William Rock. I understand there's a few members of the press here today, and if Mr. William Rock is among them, I'd like a word with him after the talk, please.
But in the midst of Yeoman's witty remarks were actually some deadly serious implications.
The computer modelers are going nuts. There's a whole community of people within DoD who do nothing but model the effects of an impact, a nuclear detonation on Earth or an asteroidal impact on Earth. The problem is they don't have any data. So what they would dearly love, of course, is a 100 million megaton impact on Earth to refine their computer calculations. There are some obvious problems with that. And so the same computer modelers are adjusting their code for Jupiter.
I have another question down here. We only had about just over a year warning of this event. It raised an interesting question. What do you suppose is the minimum warning time we would have for any comparable event on the Earth?
That's something we have been thinking about. An asteroid that's likely to strike Earth is one that we probably already know about, and so if the orbit is well enough determined, we can simply integrate forward with the appropriate perturbations on the computer. The exception to that, of course, are the comets, the long period comets that can indeed come out of the sun, take us by surprise. But these apparitions of long period comets are far less frequent than the asteroids. But if a comet did come out of the sun, it would take us, it would pretty much take us by surprise, and there's not a great deal we could do about it, but that's a very low probability event.
Just as Chodos and Yeomans predicted, the first fragment of Shoemaker Levy 9 slammed into Jupiter's southern hemisphere on July 16, 1994.
Scientists didn't know what to expect because they were just little pinpoints with tails. And some were saying that these impacts would just kind of fizzle out, that we wouldn't even see anything. And then shortly after the predicted time for Fragment A, we got a report that it was really there was a bright dot on the limb of Jupiter, so it was clearly visible, and we knew that Fragment A was not one of the larger ones.
A massive fireball erupted, creating temperatures over 40,000 degrees Fahrenheit. The plume would rise nearly 2,000 miles above Jupiter's atmosphere. Over the next 6 days, at least 20 more fragments would slam into the giant planet.
As we went down the line, some of the bigger ones, when they impacted Jupiter, were releasing, by some accounts, millions of megatons of energy when they hit. Partly because they're coming in at high velocity, but also because these fragments were likely at least hundreds of meters in diameter each.
So in your mind's eye, sort of think of A as a 1 kilometer size object, maybe E is 1.5, and then G, I suspect we're getting up to about 3 kilometers. What we're seeing is not deep in the atmosphere. While the projectile punches down deeply, all the hot stuff burps right back up to the surface. So these effects we're looking at are up on top of the normal atmosphere. They're above the ammonia cloud tops. All these wonderful features that we're seeing in here is something that's been brought up from depth that's now deposited on top.
And one of these collisions with the G fragment, which was the largest one, generated an energy of something like 6 million megatons of TNT explosive, which is 600 times the global nuclear arsenal.
If you were going to ask what's the size crater this would make on the Earth, if we're right about our estimate of the size and the energy, if it hit a continent, it would make a 60-kilometer diameter crater, thereabouts. Material that's blown out of that crater would essentially blanket the Earth with a layer of fine debris that would just block sunlight. It would just get dark all over the Earth.
It was not hard to imagine the repercussions of such an event aimed at the Earth. But there was not much of a response by NASA or the Defense Department to tackling the problem. That began to change 4 years later, after a prediction that an asteroid might hit the Earth in 2028 became front-page news.
That was a false prediction. And the scientist who made that prediction at the Minor Planet Center was basing it on really of approximations. We, on the other hand, could actually calculate the impact probability, and it was 0. No chance that this asteroid would hit the Earth. And so this became front-page news in the New York Times and many other newspapers. Here we had one prediction that an asteroid could hit the Earth, and another group, Don and myself, saying, no, it can't hit. And so there was massive confusion, and I think this was a wake-up call for NASA.
By the time of this media frenzy, NASA was responding to a U.S. congressional directive to discover 90% of all near-Earth objects large enough and potentially close enough to cause global extinction of life on our planet. Today, it's estimated there are almost 1,000 of these large objects. About 90% of them have been located. But there are many more smaller but dangerous near-Earth objects. So far, nearly 5,000 of them have been detected and designated as foes, short for potentially hazardous objects. Most of the hunting for asteroids is done by ground-based telescopes, but determining their sizes and potential for causing damage is hampered by the dim light given off by these dark objects. But an infrared space telescope, originally called WISE, has been helping to fill this information gap.
This was a mission to survey the entire sky in 4 infrared wavelengths of light. So wavelengths longer than what our human eyes can see. And the objectives of the mission were pretty simple, to just make this incredible all-sky map with a goal of seeing everything in these different wavelengths. Well, it also turned out that this project was quite unexpectedly good at sensing asteroids. As it turns out, WISE was spectacularly effective at not just observing these objects, but actually discovering new ones.
After WISE's onboard coolant needed for stargazing was depleted, it was renamed NEOWISE and repurposed as an asteroid hunter. For an infrared telescope can do something light-seeking telescopes cannot do: determine the size of an object.
This is because we're measuring the heat that comes off of the body. So rather than sunlight bouncing off the surface, we're actually seeing sunlight that is absorbed by the asteroid and then re-radiated as heat. So you can imagine that if we can measure the distance to the asteroid, and we know its brightness in these infrared wavelengths, we can actually figure out how big it is, because that sort of falls out of the equations.
But the Space Telescope's second life is nearing an end. Now in development is a successor mission.
Now we're working on the Near-Earth Object Surveyor mission. This is a new NASA mission whose objective is really to go out and map out the entire population of near-Earth objects as completely as possible. In particular, we're focusing on objects that are large enough to cause what I would call severe regional damage, meaning they're 100 or 200 meters across, and that's equivalent to something that's about a 200 megaton nuclear explosion. That's pretty bad. From my standpoint, this is a fascinating problem for a few reasons. One, just fundamentally, it's a natural disaster that we can prevent through fairly straightforward means. We can literally go look up, and if we do a thorough enough job of it, we have a chance of actually predicting whether or not there is something that's headed our way. And even if the answer is no, coast looks clear, that's a really good answer. It means it's something we don't have to worry about. So that just nice, neat solvability from my perspective is a really wonderful and rare thing in science.
Comets usually aren't shy about making themselves known. But asteroids with their darker colorations are far harder to spot. Early visuals of them were made by ground-based antennas that use radar to create ghostly images like these. The first ever close-up visit to an asteroid occurred a year before the Shoemaker-Levy 9 collisions, when the Galileo spacecraft was able to take a slight detour to capture some bonus science. A NASA mission having as its sole purpose the exploration of asteroids was achieved by the Applied Physics Laboratory in Maryland. Their spacecraft, named Near Shoemaker, flew by one asteroid and then went into orbit around a second one called Eros. This was the first time a spacecraft had ever orbited an asteroid. After spending a year observing Eros, the team decided on a daring ending to the mission: to attempt soft landing on the asteroid, something never before done, and something the spacecraft was not designed to do. Pulling off such a feat required radar science measurements provided by JPL's Deep Space Network and the expertise of JPL navigators.
Right now, we've just completed doing the last set of navigation solutions, the last optical navigation update, and we provide that solution in case we want to adjust very slightly the time of the next set of maneuvers. And the group that has done the orbit determination for Near, both radiometric using the Doppler radio tracking, as well as the optical navigation using landmarks on the surface of Eros, are done here at the Jet Propulsion Laboratory.
Okay, the cell data shows we're starting the maneuver.
Yeah, we're showing Doppler residuals are going down.
Okay.
Okay. Yeah, we're 1.7 from the landing site, Dave.
Yeah, well, let's see now
that's slant range.
Get the maneuver started.
As navigators and as mission designers, this is the kind of challenge that we want. It's a very new, exciting, and challenging kind of mission to rendezvous with an asteroid and to attempt to touch it on the surface as lightly as we can. And I think we're certainly excited to find out what happens and how gently we can put it down.
In about 50 meters per second, or 50 meters low is what Gene says.
Those pictures are really spectacular. Yeah, you guys can celebrate now.
Already popping the champagne corks. Hey, it looks like we hit less than 2 meters per second, and it did survive enough to track on the surface now.
We have two-way lock.
We have two-way lock.
After surviving the landing, the spacecraft continued operating for another 2 weeks, an impressive ending to an already successful mission. The first spacecraft to fly by an asteroid and a comet was a JPL mission whose purpose was not to chase down near-Earth objects, but to test a dozen advanced but risky technologies that larger, more expensive missions were hesitant to use. This was an effort to show that future projects could be smaller, less expensive, and capable of flying at times autonomously. At the top of the list of innovations was ion propulsion, a technology pioneered by NASA's Glenn Research Center that years before had been proposed for a mission to Halley's Comet.
Ion propulsion is designed to give fast and flexible access to the solar system for missions of the future.
The first time I heard about it was from a Star Trek episode. It was an episode called Spock's Brain, for those of you who are Trekkies. And to me, one of the neat things about working on a project like this is we're really getting to turn this fantasy into reality, and that's very exciting.
Mark Raymond, a self-professed space nerd, decided as a young child that he wanted to be a rocket scientist. And now he was living his dream, having been handed the reins to Deep Space One, a spacecraft that really did sound like science fiction. Ion thrusters make use of atoms of xenon gas, which are given an electric jolt. That disturbance results in an electric charge, and the ions shoot out of the engine at tremendously high speeds, upwards to 90,000 miles per hour. But because all of this is occurring on atomic scales, the thrust is incredibly gentle and slow. Going from 0 to 60 miles an hour will take Deep Space One 4 days.
The thrust from our thruster is comparable to what I feel from the weight of this single piece of paper in my hand. That's how hard the ion propulsion system pushes on the spacecraft. But with time, the thrust builds up, and ultimately we can achieve very, very high velocities. It's what I like to call acceleration with patience. The spacecraft is also smart enough to know how hard the sun and planets are pulling on it, and it can actually determine where it's going. An analogy I like to give for how powerful the combination of autonomous navigation with ion propulsion is, compared to what we can do today, these two technologies are like having your car find its own way from Washington, D.C. to Los Angeles, arrive at a designated parking space, and do it all while getting 300 miles per gallon.
7, 6, green board, 5.
Of course, Deep Space One first had to get off the ground.
Main engine start and liftoff.
That called for a rocket having a conventional propulsion system.
The Delta rocket with Deep Space One, testing the spacecraft technologies of the next century.
Within minutes of the launch, Deep Space One's high-risk billing seemed already in play.
When we launch a spacecraft, we calculate where it will be in the sky and what time it will turn on its radio transmitter.
Go ahead, Aiden. They're still running the receivers, attempting to acquire. BSN is green at this time.
And the signal didn't show up. That's not where you want to run into problems on the mission.
Flight 8. Go ahead. I just reported again, they still do not see a downlink signal. I copy that. Thank you very much. We're going to head and proceed with our contingency plans here. Stand by. Copy.
There were a lot more issues on that spacecraft than other spacecraft I've flown since.
Go ahead. I just reported again, they still do not see a downlink signal.
A lot of things go into that because we're kind of pushing the boundaries. We're building these things for the first time.
Also be advised that the station is currently experiencing some receiver problems and they do not see a signal. I copy. Thank you.
This moment of flight jitters eventually passes when the spacecraft reports that it is alive and well. The team spends the next 2 weeks preparing for turning on the spacecraft's ion propulsion system for the first time.
This was the big day when we were actually going to light it, go to warp power, emit that cool blue beam, and get underway with our powered flight.
At 1859.00.
Ace, this is flight. You are go for radiation of India Charlie 018, X-ray 01 at 1859.
This is the moment that is hoped will change the future of deep space exploration.
Right, once accelerated, shifts down some. Real high frequency stuff.
It'd be interesting to see if we see the Doppler, see stuff in Doppler.
It almost bet on.
That's right.
Seconds.
This will change to true. It will go through the startup sequence.
Unit 1 team, this is Mission Director. Prepare for warp speed. Yeah, right.
So we had all these people here. We sent the commands to the spacecraft, and sure enough, right on schedule, the spacecraft went through its own final procedures to start the engine, started the engine. It worked great.
There it goes.
There it goes. All right.
Congratulations, Jack. Everybody.
Congratulations.
Good job. Not me. You guys.
Hey, Jay.
We lit off.
Curve you're looking at is right there. 0.5.
Jason.
There it is.
Everybody in mission control was all excited. People in the hallway were all excited.
Oh, we're in standby. We had 20 recycles.
We're seeing TDC mode.
Well, the spacecraft had thrust for 4.5 minutes and then stopped. And so we immediately started trying to diagnose the problem.
I think we need to caucus on this. Roger that. Please consider your evaluation for restart.
People, excess people filter themselves out of the room. A lot of noise, a lot of crowding.
After regrouping, the team tries restarting the engine.
Thank you, Flight. This is Mission Director. You're authorized to radiate. Command DSN File Uniform Charlie 065 Alpha 01.
All units be advised, the thruster is off again.
Time limit, and we shut down and we're now in standby.
Roger that. Is there an evaluation of what caused the sequence of events?
There's discussion going on right now about that. We'll get back to you.
So every time it arcs, the high voltage cuts off and then goes back on automatically.
Right, to try to clear the fault. That's good for
A number of attempts are made, all with the same result.
Shut down.
Did it happen right away this time, guys?
Each time that happened, our spirits went down a little more. Ion propulsion was the primary objective, and here we were unable to get more than 4.5 minutes of thrust. And in fact, our minimum success criterion for Deep Space One was to thrust with the ion propulsion system for 200 hours. Well, we still had another 199 hours, 55 minutes, and 30 seconds to go.
While disappointing, these kinds of shutdowns didn't come as a total surprise. Similar events have occurred during lab tests.
Plasma wave is, we're going to get the search coils come around and see how they correspond. While the arc and you were burning for a while. It's probably a noisy burn right there. Because it should clean up to be fairly clean once the accelerator works right.
There may have been just a small piece of contamination in the thruster, in the ion engine, left over perhaps from launch when the whole spacecraft was shaken violently.
Can we set up the times relative to what we're seeing?
Well,
We did a number of things, including turning the spacecraft so the engine would point toward the sun and away from the sun. That would loosen this particle so it could just drift away.
After 2 weeks of using the sun to alternatively heat up and cool down the spacecraft, the propulsion system was tried again. The era of ion propulsion had arrived.
Over the course of the mission, we put it through its paces, we tested it thoroughly, we showed we could count on it to propel the spacecraft, we could navigate with it. It was wonderful. That meant that many subsequent missions that would have been impossible without ion propulsion then were possible.
What followed was a whirlwind of testing the other technologies on board. And only 9 months after launch, with almost all of the mission's objectives met, the team was eager to fly by an asteroid named Braille.
That was a great way to take all these new technologies and show that you could do planetary science.
You have to say it in French.
We're out there, let's go use all this fancy stuff to go take pictures of something.
The asteroid Braille was co-discovered just 6 years earlier. One of the two co-discoverers was Eleanor Glow Helen, a JPLer and a pioneer in asteroid hunting. That the asteroid was found was an impressive feat, for the asteroid was so dim that Deep Space One was almost unable to spot it. And just hours before the encounter, a software bug caused the spacecraft's computer system to overload, requiring a reboot.
The fact that the spacecraft was very temperamental, like, almost made us not able to do that encounter. We went into safe mode the morning we were supposed to do this flyby. I got a text message. Back then, you know, we didn't have cell phones. We just had these pagers, but the pagers were fancy ones that you could get a text message on. I got this text message that said, "We're in safe mode," and I'm like, wait, the encounter is tonight. It takes 3 days to recover from safe mode. Oh my gosh, I better get into work.
We sample about every...
Racing against the clock, the team beamed up new instructions. The last command was transmitted with only minutes to spare. The science results were modest. The few images of the asteroid were taken at a further distance than intended, causing them to appear out of focus. Still, this had been the smallest celestial body ever targeted by a spacecraft, coming within 17 miles. An impressive accomplishment that convinced NASA that the mission was worthy of a second shot. The next target would be a comet. But in November 1999 came the most serious crisis of the entire mission. The spacecraft's star tracker, which looks at stars to determine the spacecraft's orientation, ceased working. Without it, the spacecraft was left in a state of confusion, knowing neither up from down nor right from left.
The star tracker on Deep Space One is responsible for telling the spacecraft how it's oriented in the zero gravity of space. We know where it is and where it's going, but we can't tell where it's pointed without the star tracker.
The spacecraft, for all intents and purposes, could accomplish nothing of value without the star tracker. There was no reasonable, rational prospect of being able to continue the mission. But I didn't want to give up that easily.
Normalize all these to one number and decide what to add or subtract.
The team started working on ways that we could rescue this spacecraft from across the solar system. With a fatal, catastrophic failure for which there was not even a concept for how we might recover. All we had to work with was what was on board the spacecraft, plus, of course, ones and zeros that we could send to it.
VSS 45. VSS 45.
There followed months of very, very long hours, every day, constant stress, this feeling of, I want to get this spacecraft working again.
There ended up being only one possible fix: to send up new software that would reconfigure the spacecraft's camera to do double duty as a star tracker and a camera.
The science camera was not designed to do that and had a much narrower field of view. The star tracker has a giant, wide field of view that can see a significant part of the sky. The science camera is sort of like trying to drive your car looking through a soda straw. Basically, what we needed to do from then on was pick a direction that we wanted to thrust, find a star near there, and then thrust at that star for a while. And then after a while, the navigators would tell us, now we need you to point the thrust in this other direction. Like, oh, okay, let's go find a star over there that we can thrust at.
Like a sailboat tacking with the wind, Deep Space One zigzagged its way to a comet named Borrelli. The closest approach would be on September 22, 2001. 11 days before then was 9/11, the day the United States was attacked by 4 hijacked planes.
It just turned the world upside down. Personal emotions about it was, by gosh, we are going to accomplish this thing. We aren't going to let this stop us. The lab is completely empty. There's guards everywhere with guns, there's guards with shotguns at the front gate. And, we have special permission to be the only people allowed on lab because we have this operations work to do. It was very emotional. Said a lot of people had their American flags. I'm a volunteer for the JPL search and rescue team. I had some inkling of what was going on in New York, so I wore my search and rescue helmet that day.
We had faced so many difficulties. We'd had to make so many decisions. And, Deep Space One had not been designed or built to encounter a comet. And the encounter at Borrelli didn't go the way we expected. Instead, it was perfect. Years of nursing along this damaged, wounded spacecraft. It was pretty rewarding.
Scientists were elated with what were then the highest resolution pictures ever taken of a comet. The stubborn team of engineers could also take pride in having opened up a new chapter in robotic space exploration. Three months later, with the spacecraft running low on fuel and no other science destination within reach, the mission was officially declared over. Today, Deep Space One, a small spacecraft operated by a small team with big hearts, silently circles the sun.
Perfect, okay. See ya! We're not?
It is nice up here.
Correct. Copies. You're clear to run.
Okay. Here we go.
During the same year that Deep Space One flew by asteroid Braille, NASA's first mission devoted exclusively to comet exploration was underway. The vehicle wasn't a balloon, although this one was part of a critical pre-launch test. The main goal of this mission, called Stardust, is to send a spacecraft out to capture samples from a comet and then bring them back to Earth. What's been pushed out of the balloon is a model of the capsule that is to contain the comet particles. This drop test is to determine how hard a landing the capsule can withstand. The landing area is the Dugway Proving Grounds, a remote military facility in northwestern Utah, The winter weather makes for a cold outing, but the wet ground will hopefully make for a soft landing.
It wasn't traditional. They landed right on the road.
Oh, right.
A comet sample return mission was first proposed for Comet Halley. The scientist involved in that original proposal, Don Brownlee, had never let go of the idea. And the comet that's been chosen to sample, Wild 2, has an unusual history, as comets go.
We have this wonderful situation. The comet came from the edge of the solar system, came into the inner part of the solar system where we are, and then we sent a spacecraft out halfway to Jupiter to meet this thing. So it's really kind of a sort of a magical situation, I think.
Wild 2 is believed to be as old as our solar system, and it is thought to contain some of the most pristine and pure materials out of which the solar system was formed. That made for a convincing case to greenlight the mission. And the price tag didn't hurt its selection chances either. This was one of NASA's early faster, better, cheaper missions. The goal was to fly a spacecraft for less money and on a faster schedule. And Stardust promised just that. The spacecraft is a straightforward design having few bells and whistles. It is to be powered by solar panels, but no spacecraft has ever been asked to travel as far from the sun using solar energy as this mission will have to go. And no spacecraft had ever flown as close to a comet as was planned for Stardust, which is why the spacecraft is front-loaded with bulletproof shielding.
We're playing a game here. We want to go close as possible to the comet to get the best images and to collect the most amount of sample, but we don't want to get hit by large enough particles to destroy the spacecraft.
Stardust's most unusual feature is its comet dust collector. It resembles a tennis racket full of ice cubes. But this blue material is an ultralight compound called aerogel. Sometimes referred to as frozen smoke, it's a solid that is 99% air. JPL researcher Peter Sue made a career out of finding ways to use this strange material.
Aerogel, although it's very fragile, but it has very high compressive strength. And let me demonstrate to you, this piece of aerogel weighs about 10 grams. This piece of plexiglass is about 50 grams. That's already 5 times the weight. This is 1,000 grams. This is another 1,000 grams. It's 2 kilograms. So this is 2,000 times its own weight.
While aerogel can carry more than its own weight, it is also porous enough to capture intact comet particles that are moving faster than a bullet. A year after its launch in 1999, Stardust gathered in the first 2 samples of interstellar dust. Then it was on to a full dress rehearsal of a comet encounter by flying by asteroid Anne Frank. To protect the spacecraft, Stardust was kept at a safe distance of over 2,000 miles. Still, engineers were delighted with the test. And scientists even got a far-off peek at the asteroid.
Half-pixel residual.
Another year passes before the encounter with Wild 2, and as the day nears, the comet isn't cooperating. It's dimmer than expected. And that likely means there will be far fewer dust particles to collect than wanted.
As far as the
brightness of the object, the photometry is concerned, we're somewhere between 5/7 and 5/10 the amount of dust that we expected to observe. Yeah, there's less light coming from the thing this time, less flux.
The only way to collect more dust is to fly closer to the comet. But flying closer increases the risk that the mission could be lost.
Now, originally, these observations we weren't going to use to change our plans. We were just going to use to confirm that we're still in the ballpark.
This meeting offers a rare look into how such pressure decisions are made in real time. The encounter is only 3 days away. At the table are JPL engineers, navigators, scientists, a NASA headquarters representative, and by phone, the spacecraft contractor Lockheed Martin. Given the concern that debris shedding off the comet might ruin the encounter or even destroy the spacecraft, the question on the table is how close should the flyby be?
I didn't make too much noise about going to 300 at the time because there is a chance that we might lose all of the images if we go into 150.
If we do go into 150, pretty much are close to collecting the particles, but if we go into that close, there's about a 4 times higher chance we will lose the image sequence during the flyby. So what's science assessment?
Well, my recommendation is we target for 250, which is a modest correction. This is better than sticking at our target value of 300 kilometers we did in the past. I'll use Sham's golf analogy. We're approaching the hole, and we're doing tweaks as we're coming in.
And there's still a probability it'll work. I mean, it's not saying that it won't work. It just.
What do you mean?
Yeah, but
what do you mean probability?
Well, I don't know. I mean, I'm not saying it's an absolute failure. I'm not saying it's an absolute success.
You know, if we're opening up, we're exposing ourselves to some new risk we haven't imagined, then that's really a stupid thing we'll always be crucified for. And if we lose imaging close in, we take a gamble. We've always known that the comet could disintegrate at any minute. It could turn off. It could turn on. It's an uncontrolled beast.
Okay, I think another data point is independent of science. I will not support a 150 kilometer flyby. I will be dead set against it.
So your recommendation is 250?
250.
After all this back and forth, the team is in accord. The trajectory will be changed to bring Stardust 50 kilometers closer to the comet. If Vilt 2 has any more last-minute surprises, there are preloaded contingency plans aboard Stardust that hopefully will allow the spacecraft to respond on its own.
Hey, Tom, you're really fading out. You've been breaking up now.
Yeah, we got a lot of static here.
Good morning. This is Stardust Mission Control at NASA's Jet Propulsion Laboratory in Pasadena, California.
It is now 1 day after New Year's Day 2004. The time for the comet flyby has arrived.
After nearly 5 years and 2 billion miles of space travel, Stardust is about to perform a flyby of comet Vilt 2.
It is also just 1 day before the landing of JPL's Opportunity rover on Mars. A busier time would be hard to imagine.
All station started systems. This is closest approach at this time.
We are going into an unknown environment. No spacecraft has ever gone this close to a comet.
Is that consistent with the 4-degree roll, which we expected to see?
The moment of closest approach passes. Stardust is still sending back. preparates its capsule, which will have to endure the intense heat of re-entry through the atmosphere. Next, a parachute is to deploy, which should provide the capsule with a soft landing in Utah. Helicopters are to retrieve the capsule. Then this cosmic cargo is to make its way to a lab at the Johnson Space Center in Houston for detailed examination. That's the plan. But a parachute had failed to open on another JPL mission called Genesis. Its capsule, containing samples of the solar wind, slammed into the Utah desert. Fortunately, enough particles survived the hard landing to be useful for scientists. But no one wants to see a repeat of such a shattering experience. After a journey of 7 years and nearly 3 billion miles, the capsule re-entered the atmosphere at a speed of nearly 29,000 miles per hour, the fastest re-entry of any human-made object on record. Witnessing the spectacular entry were scientists flying aboard a NASA Ames research plane.
17 degrees aft.
The blazing capsule, filled with comet particles, now looked to be itself a comet.
Okay, we have confirmation of a main chute.
All stations, main chute is open. We're coming down slowly.
Stardust was the first sample return mission since Apollo astronauts brought rocks from the moon back to Earth. Inside the capsule were thousands of samples of comet and stardust that were shared with scientists worldwide. These particles, the only known samples from the outer solar system, were once part of a primitive, ice-rich body that formed well beyond Pluto. But surprisingly, many of the rock dust particles were similar to those found in primitive meteorites that formed close to the Sun. Apparently, these particles were transported to the distant comet-forming area in the outer regions of our solar system. Another discovery was the presence of the amino acid glycine, a fundamental building block of life. Its detection has added credence to the idea that the materials necessary for life to arise may be spread in abundance across the universe. While Stardust brought back samples from a comet's surface, JPL's Deep Impact mission was designed to hit a comet in hopes of revealing what materials reside in its interior.
5, 4, 3, 2, 1. We have ignition and liftoff of a Delta II rocket carrying Deep Impact, NASA's journey to unlock the mystery of the solar system's origin.
And the air starts have ignited.
Being launched into space are actually two spacecraft, the Deep Impact mothership and its cargo, a small washing machine-sized impactor to be released to collide with a comet. The two spacecraft were built by Ball Aerospace, with JPL responsible for management oversight and creating the especially complex software required for the mission.
We had 12 months to complete the assembly of the prime spacecraft, complete the assembly of the impactor spacecraft, go through the entire environmental test program, fix the flight software, fix the fault protection, fix all the bugs that we found along the way, and figure out in parallel how to hit the comet
Hitting a comet was something no spacecraft had ever done. And to have any chance required creating computer simulations at JPL. As often as not, the early simulations resulted in misses. And then, 2 months before launch, a near catastrophic mistake was made.
There was that black day in November where somebody came in and accidentally deleted all the files. Sequences that we were working on for post-launch, encounter, everything. Gone on one night. Deleted because somebody thought they needed space on a server. And it was like, how in the hell do we ever recover from this?
The solution was to work intensely long hours, and the pressure didn't let up post-launch. The journey to the comet, named Tempel 1, was a short one, just 6 months. When only halfway there, the comet was already in sight. The JPL flight team barely had enough time to settle in before the encounter was upon them.
Normally it takes many months to launch a spacecraft and check it all out in flight and learn its idiosyncrasies and get it all calibrated and working good. And so to launch the spacecraft and only 6 months from then have an encounter was very challenging. We were sleeping in our offices level of working hard. And I came in one day, to my office, and I had my bedding all set up, and somebody had turned down my sleeping bag and put a mint on my pillow and left a little note that said, "Complimentary turn down service." It was, it was crazy, crazy days.
And what Deep Impact was expected to do sounded a little crazy too. What's been described as hitting a bullet with a bullet. After the impactor is released, its onboard navigation system has to visually find the comet in order to execute 3 targeting maneuvers. 3 chances of zeroing in on the comet.
The impactor, once we release it, has an auto-nav system like we introduced with Deep Space One, and it locks onto the comet and tries to make sure that it's going to hit it. And it makes that first correction based on information from a long ways away. And so each successive correction as we get closer is going to be better and smarter. And so there wasn't a lot of actual commanding going on. It was mostly we're watching the spacecraft to make sure nothing funny happens.
All of this is to occur on the 4th of July. But Comet Tempel 1, not to be outdone, has already been shooting off its own celestial fireworks. Comets are known to sometimes have sudden outbursts, releasing massive amounts of gas, ice, and dust that briefly increase their brightness. A concern is that if Tempel 1 decides to flare up during the encounter, the impactor's auto-navigation system could become confused. Worst case, the impactor might miss the comet entirely. It's not what the team wants to happen on a national holiday.
Mission, impactor flight, all impactor spacecraft subsystems green at this time.
It is now the 4th of July. The time of impact is 90 minutes away.
We are turning to the burn attitude. Target ID 6.
Copy, thank you.
The first impactor trajectory maneuver, or ITM, is underway.
Impactor flight, impactor prop. Flight prop.
We see TCM thruster firing with accumulated on times increasing.
Copy, thank you. Flight confirms your go to radiate. Roger, on my mark. 3, 2, 1, mark.
Cat bed temps look as expected. The accumulated on time is about right as well. And we'll give you a more full report later.
Copy, thank you.
The comet is not yet done with its surprises.
What's the most difficult issue that's confronting the team right now then?
Right now it's the comet, which is why we're going there. It's presenting a very strange shape to us. We've been watching it all day as we get closer. We initially thought that this thing was something like a pickle. As we're getting closer, it looks like it's more like a banana. And the latest resolution that we have in the rotation that it's going is that we're looking at the end of it, and the end of it is basically triangular. So it all depends on what that comet does and what type of face it presents to us, and we have to solve for that. So that's the challenge.
And it appears that this has been quite a temperamental comet. Over the last couple of days, we've seen several outbursts from it.
Yes, that's true. We have seen the actual jet outbursts that brighten it, so it's very exciting for the scientists.
And nerve-wracking for the engineers. And even worse, the results of the first impactor maneuver were not what was expected.
It was the biggest movement off the comet we have seen, period. Even more than any of the simulations.
And that knowledge raises the possibility that deep impact might miss the comet entirely.
And the chatter is starting up that everybody's really worried on whether we can correct for that and come back in again.
Flyby AutoNav.
Go ahead.
The AutoNav flyby B-plane is 365.8 by 341.0 with a time of flight correction of less than 1 second at this point. Flyby AutoNav.
Go ahead.
I'd like to add to that B-plane information by saying we're about 1 kilometer off from the ground nav solution.
I was an extra set of hands, so I was basically moving around when issues would come up. As it turned out, that first correction kind of took us off in the weeds a little bit. They're aware of it and worried about it, but they're also like, it's supposed to bring us back. It was hair-raising.
After ITM-2, we have 6.5 kilograms of fuel remaining, which equates to 31 meters per second.
Flyby thermal. Request to go offline for 2 minutes.
Dan, sitting next to me, he looks like a ghost because all the blood just drains out of him. And he says, Care, I need to go off net for a few minutes. He goes off net, then he comes back 5 minutes later, and he looks better. And, he kind of leans over to me and whispers to me saying, I just threw up. Because he was so sick from how big the ITM was, and he wasn't sure whether we'd come back in again or not. We can't do anything about it. All we can do is trust the work that we did.
We've seen the comet in all 3 cameras. We've seen it in the impacting camera, the 2 cameras on board the flyby spacecraft as well.
Providing live commentary during the event is Don Yeomans. Yeomans is blissfully unaware of the concerns over trajectory maneuvers, but he has his own reasons for being anxious.
They needed some stooge to get out there and talk to the media. Either it was a smashing success or a horrendous failure. And so I was just worried sick that I would get this question after the fact that, Dr. Yeomans, NASA has spent $240 million on this deep impact mission, and you guys missed?
So this is our best image to date. It's only going to get better, much, much better. Now it looks bright, but it's actually a very jet black object that is being overexposed to show the light. It's sort of rotating around an axis that is more or less up and down. And so you're looking at the small end of the pickle here. It's a 9-mile pickle, mind you.
Impact flight, we've begun ITM-3.
Impactor flight, impactor prop. We also see TCM firing for ITM-3.
Copy.
The last of the 3 thruster burns is underway. Nothing more can be done.
Mission, this is flyby Pulpitech.
Go.
Reporting on our last enabled state change for flyby, final imaging before shield mode. We have a disable of all ADCS performance. Basically, we're left with what keeps the hardware talking. ADCS, you're on your own.
Copy.
There are some of the images coming down from the spacecraft.
Oh, my, look at that. Looks like we've got...
No longer a pickle, more of an eggplant.
Yeah, now we're moving from the pickle to the eggplant here, and it looks like we have some clearer surface features over there on the right. A dark depression, perhaps?
Look at the jets. Look at all the jets. Yes.
I have a little voice in my ear that tells me that we can put up the impact camera image in our monitor right now.
Okay. This is the impactor image, the spot where we're headed for impact. And the spacecraft's doing remarkably well for something that's about to vaporize. It's getting closer. We may be getting some serious dust hits. Our brave little spacecraft is in a very hostile environment here. We're going not only faster than a speeding bullet, we're going about 10 times faster than a speeding bullet. And that puts Superman to shame. We're expecting to lose the spacecraft any minute here. But it's doing one heck of a job just before checking out.
Flight, this is Telecon. We have lost the block.
Copy that.
The mothership, flying underneath the comet, recorded the aftermath. The impact was far more dramatic than expected, generating a brilliant flash of light and an immense fluffy cloud of ice, dust, and gas. That the comet's surface was so extremely fine, weaker than powdered snow, was a major surprise. This was no ice cube comet.
A crater and ejecta that's just enormous. It's considerably brighter and considerably more material coming off than I thought.
Also unexpected was the sizable amount of organic material that was detected. Yet another indication that comets and asteroids may have seeded the early Earth with the building blocks of life.
We've got all the data we could possibly ask for, and the science team is ecstatic. And not a one of them can believe they're being paid to have this much fun.
Two, 3 o'clock, 4 o'clock, rock. 5, 6, 7 o'clock, 8 o'clock, rock. 9, 10, 11 o'clock, 12 o'clock, rock. We're gonna rock around the clock tonight.
There was more fun the very next day. The Comets, the original backup band for Bill Haley and the Comets, were on a nostalgic tour and made a surprise visit to JPL to offer their musical congratulations. Word of their presence quickly spread, and soon a spontaneous celebration erupted. These comets were rocking before there was even such a thing as a space age. And they still knew how to make an impressive impact of their own. Years before, after Voyager's final planetary encounter, the legendary Chuck Berry had played on this same spot. Now JPLers could also boast of having rocked away to the sounds of rock and roll's very first band.
We love you all!
Deep Impact's impactor was no more. But the mothership had survived, and the team was eager to sign up for another mission. 5 years after the Temple 1 encounter, Deep Impact flew by a second comet, Hartley 2. JPL's Stardust mission was also repurposed. It revisited Temple 1 to see the aftermath of Deep Impact's collision with the comet. And Deep Impact was followed up by NASA's Goddard DART mission. The spacecraft flew into a tiny moon orbiting an asteroid to demonstrate how they might be moved slightly off course. Keeping track of asteroids and comets is an international effort. A Chinese lunar orbiter flew out and passed by an asteroid. The European Space Agency's Rosetta mission, with a JPL science instrument on board, accomplished the first mission to deploy a lander to a comet's surface. And NASA's New Horizons mission holds bragging rights to the most distant object ever explored, following its flyby of Pluto. After JPL's innovative sample return missions, Japan's space agency has gone a step further. Their Hayabusa 1 mission landed on an asteroid, collected tiny grains of material, and brought them back to Earth. The Japanese repeated this remarkable achievement a second time, a decade later. NASA's OSIRIS-REx mission has also collected samples from an asteroid, which are now on their way home, scheduled to arrive in 2023. The technology advances from JPL's Deep Space 1 mission were put to use on the laboratory's Dawn mission. Using ion propulsion, Dawn was able to orbit 2 worlds in our solar system for the very first time, Vesta and Ceres, the largest objects in the asteroid belt. Recently launched is NASA's Lucy mission, that is to visit asteroids that share the orbit of Jupiter. And Psyche, a spacecraft managed by JPL, will soon be on its way to an asteroid made not of rock or ice, but metal. Flying a spacecraft propelled by a solar sail finally succeeded in 2019 with the Planetary Society's tiny LightSail 2 spacecraft. This publicly funded mission stayed in Earth orbit for 3 years before re-entering the atmosphere. A more recent NASA solar sail mission failed to deploy. All of these missions are about learning more about asteroids and comets, so that we might better defend against them. One element of planetary defense is called mitigation. What might be done should a near-Earth object threaten our planet.
There are lots of mitigation ideas. Putting a solar sail on the asteroid, throwing rocks off the surface, There's gravity tractors. Just using the gravitational attraction between the asteroid and the spacecraft and thrusting on the spacecraft, you could move the asteroid off its Earth impacting course if you had enough time. There's the impactor, which would be my favorite because it's so simple. And DART mission and the Deep Impact mission demonstrated the fact that we can run into these targets if need be. In a worst-case scenario, if you had a large object and little time, you could use a nuclear explosion. Much like the Armageddon movie in '98. We have to bring back Bruce Willis. But the three most important things for mitigating a potential Earth impact are to find them early, and find them early before they find us.
And a recent example of that need occurred in 2013. It was a year when it was known that an asteroid named 2012 DA-14 would be passing extremely close to Earth.
A very close approach. And it was going to come within the ring of geosynchronous satellites. So that's really close. It's almost scary close in the sense that you want to see whether it's going to hit any satellites. But we knew that it would not hit. And we had been tracking this for about a year and predicting this close approach. So it was an event. And we had a NASA TV show hosted here at JPL in which we were planning to talk all about the close approach. There's nothing to worry about, going to come really close, and these things are rare, but we know that it's not going to hit.
Now, DA-14 is not a threat. It will not hit the Earth. Scientists say the closest it will get...
Well, the night before that, what should happen, but on YouTube, all these reports of a massive fireball in Russia, in the city of Chelyabinsk. A lot of the videos were from dash cams. And they showed a really massive fireball coming in that was clearly much brighter than the sun. So that's a major event. It became evident that our little story of an asteroid coming really close to the satellites was being totally preempted.
Well, right now I am joined by Paul Chodas. And Paul, we probably have to address right off the top this meteor that hit Russia overnight.
What an exciting day. We feel like it's like in a shooting gallery here. We have two rare events of near-Earth objects approaching the Earth on the same day.
What can you tell us about this? Anything at this point?
First of all, the two events are unrelated. The meteor over Siberia and over Russia was not related to the asteroid 2012 DA, and they're not in the same trajectory, the same orbit. It's simply a coincidence that they happened to hit and come near the Earth at the same day.
How big was this meteor?
The meteor, we think, was around 15 meters in size, which is about 1/3 the size of DA-14 itself.
Okay, so it's much smaller.
Much smaller, and you can see what sort of destruction and shockwave that a smaller asteroid can produce. It's like Mother Nature is showing us what a small one, a tiny one really can do.
The energy released is estimated to have been equal to a TNT blast of 500 kilotons. Many times larger than that of the atomic bombs used in World War II. The shockwave blew out windows, damaged buildings, and caused upwards to 1,500 injuries, including reports of skin burns and temporary blindness. A question raised was, why wasn't this asteroid detected? The answer was that it had approached the Earth from the direction of the sun. Looking towards the sun is a blind spot, not only for our eyes, but for telescopes too. To have had an advanced warning of the Chelyabinsk meteor would have required spotting it in a darker part of the sky. The last time an event like Chelyabinsk occurred was more than a century ago. But the fact that such a small object, believed to have been no larger than 50 feet in size, can cause such damage is yet another warning issued by Mother Nature. For there are likely millions more near-Earth objects of this same size yet to be found. So how should the world prepare for the possibility of a major impact by a near-Earth object? In the United States, various government agencies annually take part in tabletop exercises in which they must react to a fictional near-Earth object impact. The realistic schemes are devised by JPL's Center for Near-Earth Object Studies. The mastermind for creating these fictional threats of doom is the center's mild-mannered Paul Chodas.
The conference is called Planetary Defense Conference. They have been going for 15 years now, more, almost 20 years. At each of these, we typically have exercises where we kind of ask ourselves, what would happen if? And at many of these, I've put together scenarios of an impacting asteroid heading for the Earth, and simulating that and calculating what we would know when.
One exercise, played out in 2021, began with a new asteroid of an undetermined size being discovered by a ground-based telescope. It is some 35 million miles away, about a third of the average distance to the Sun. The discovery is relayed to the Minor Planet Center in Cambridge, Massachusetts, which collects and catalogs small solar system objects. News of the asteroid is then passed on to JPL.
Paul Chodas. And we pick that data up. We do that routinely. All of this is automated, so we would compute its orbit as accurately as possible, and the uncertainties in that orbit, which initially would be huge, and determine whether or not there's any chance of impact. Now, for this particular scenario, that impact is only 6 months away. And so our software would immediately detect the fact that this could hit the Earth. We need more observations.
As it goes past. So it's pretty cool. Oh, we have a lunar eclipse.
A mere 6-month lead time is dire news. But initial calculations show that the probability of an impact is low. About 1 chance in 2,500. But to have any confidence in this estimate, more observations are needed.
And so, depending on where the true impact trajectory is,
for a week, astronomers across the world aimed their telescopes at the night sky. And with each observation, the odds of an impact increased.
What is it, 400-day arc now?
Continuing to track it gives us better and better idea of whether or not it might impact. But there's the other matter of knowing, well, what are the effects of that impact? And that depends on the mass of the asteroid, which is basically its size. But we never really know its size accurately unless we have something like radar on it, or we visit it with a spacecraft and take images of it.
These two options aren't feasible. Radar is only effective when an asteroid is near the Earth. By then it will be too late. And with the impact just 6 months away, there's not enough time to launch a spacecraft to make up-close observations. So virtually nothing will be known about the asteroid's size and the damage it might cause.
The risk corridor. Let me move ahead through a lot of this stuff to...
By the end of the first week, the probability of the asteroid hitting the Earth has climbed to 5%, or 1 chance in 20. As to where the impact may occur, the potential areas are at first literally all over the map, covering 2/3 of the Earth's surface.
Large swaths of the Earth are at risk, initially. And it's our job to get a better and better orbit to narrow that down so that we know where the asteroid is headed and we can isolate the region of the Earth where it might hit.
To make matters worse, for the next few days, new observations by ground telescopes aren't possible due to the glare of a full moon. Astronomers use this time to search through their archives, looking for any possible past signs of the asteroid buried in their records. Meanwhile, for policymakers, a major question is what information should be shared with the public and when.
The data on which we base our orbit calculations are really international in scope, and they're available to all around the world. And the other orbit computers can run their calculations, maybe not quite as elaborate as ours, but come up with similar results. So it would be very difficult to kind of sit on this impact prediction and not tell anyone.
The group's suggested headline doesn't mince words. Newly discovered asteroid poses risk of Earth impact in 6 months.
These are just nominal.
Another week goes by. The effort to comb through past data has paid off. It shows that the asteroid had passed by unnoticed 7 years before. With this orbit data in hand, a better prediction of the asteroid's flight path can be constructed. The news is not good. The impact probability is now 100%. The potential target areas are narrowing too. A new headline is prepared. New observations confirm asteroid will impact in 6 months. The regions at risk are Europe and North Africa.
In this particular scenario, with only a few months of warning, it's really impractical to think that we could deflect this particular object. So then this scenario was designed more or less to deal with the civil defense issues of what you would do to evacuate areas once you knew more or less where it's hitting and once you knew more or less its size.
If the asteroid is as large as 160 feet, the impact is expected to be as powerful as the atomic bombs used in World War II. If it is 1,000 feet in diameter, destruction would be measured on a continental scale. A half-mile wide asteroid could mean global catastrophe. Meanwhile, an international effort has been exploring how a space mission might protect the Earth.
We did talk about, what we could do to mitigate and whether there would be any possibility. But with 6 months, there's not much.
It's soon apparent there's not enough time to attempt a deflection technique that might knock the asteroid off course. The only option left is to try to launch a spacecraft armed with a nuclear explosive device.
We have engine ignition.
And because so little is known about the asteroid, the recommendation is to send as large a bomb as possible, and then hope for the best. Of course, this assumes that a spacecraft capable of being quickly armed with a nuclear device is possible. Currently, no such rapid response capability is known to exist. Meanwhile, observations by the infrared space telescope NEOWISE provide the first information about the asteroid's size. It is likely no more than 500 feet in diameter, and the impact zone has narrowed down to a region mostly within Germany, Czechia, and Austria. Among the cities at risk are Munich, Prague, and Vienna. It is now 6 days until impact. The asteroid is 4 million miles away and now in range of JPL's radar imaging assets. The size of the asteroid is further refined. It is somewhere between 300 and 400 feet in diameter. Estimates of how powerful the impact could be range from 9 to over 150 megatons. To give those numbers meaning, a single megaton contains the energy equivalent of 1 million tons of TNT. The day of impact arrives. The asteroid enters the atmosphere at the precise time predicted. The world can only await what will follow. Today, we know of more than 1 million asteroids in our solar system, and thousands are found every year. Most reside in the asteroid belt between Mars and Jupiter, and they pose no threat from that location. Of concern are asteroids that are nearer, especially those that can cross Earth's orbit. It's believed that 90% of the near-Earth objects that could cause a global catastrophe have been found. But there are estimated to be thousands of asteroids large enough to cause severe damage over a wide region that have yet to be discovered. But that knowledge doesn't seem to keep asteroid hunters awake at night.
These events are so very unlikely to happen that it's not something that we lose sleep over. In fact, I feel more confident in the sense that we have capability to deal with them.
Out of the tabletop exercise, there was one big takeaway: greater awareness of the extreme challenges that come with a late discovery.
The bottom line of that exercise is that that asteroid could have been found earlier, at least 7 years earlier, with a better asteroid survey, a more sensitive survey, such as NEO-Surveyor.
Had a more robust detection system been in place that included a space infrared telescope, this fictional asteroid might have been known years earlier, allowing for a number of mitigation options. There could have been time to build and launch a reconnaissance spacecraft to determine the asteroid's composition, mass, and size. With that knowledge, a plan of action to divert the asteroid could have been devised. So what is the best line of defense? The answer is worth repeating.
The primary goal for defending against near-Earth objects that are on Earth impacting trajectory is to find them early, and find them early before they find us.
Between 1968 and 1972, America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind: the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there is no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the moon days later. Once this burn is complete, the upper stage of the SLS is jettisoned and the crew aboard Orion coast for several days toward all that awaits them at the moon. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach: pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit and once again to sling the spacecraft around the moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our moon and prove that together we are ready to go beyond.
My dream is to work on the surface of the moon.
How do you think of those upon whose shoulders we stand?
I really appreciate that legacy, and I try to work my hardest to honor it. That baton has been passed generation to generation.
It is pretty amazing, though.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
3, 2, 1, 0. All engine running.
Let's go.
We have been given the scientific knowledge, the technical ability, and the material to pursue the exploration of the universe.
Attempting to land on the moon to return the United States to the moon for the first time in 52 years.
Nova-C uses an environmentally friendly mixture of liquid methane and liquid oxygen.
Incredibly challenging thing like landing on the moon forced us to innovate.
Intuitive Machines has built an entire space program to support these CLPS missions. The company completed its lunar lander in a new facility at the Houston Spaceport, just down the street from NASA's Johnson Space Center. It's an autonomous Nova-C class lunar lander named Odysseus.
Lunar lander arrived at Kennedy Space Center in Florida back in December. Since then, teams have been integrating the spacecraft to Falcon 9's second stage in preparation for launch.
Go IM-1 and the Odysseus lunar lander.
Falcon 9 has successfully lifted off from Pad 39A at Kennedy Space Center. An incredible sight to see.
Odysseus lunar lander separation confirmed.
Our Nova-C lunar lander has successfully separated from the second stage of the launch vehicle, autonomously commissioned, and made first communications contact with Nova Control.
Our approach for landing is actually very similar to what Apollo did, which should be no surprise because the physics are very much the same.
Let's honor this momentous milestone and prepare for the challenges and triumphs that await us on our lunar journey. You're taking a live look into Intuitive Machines' Nova Control in Houston, Texas, where flight controllers are preparing to start the landing sequence for the IM-1 mission. Our mission and activity directors are sitting closest to the large monitor inside Nova Control, and they're supported by 10 additional flight controllers surrounding the circular Mission Operations Center. Good afternoon and welcome to our coverage of the descent and landing of the IM-1 mission. I'm Josh Marshall, Communications Director of Intuitive Machines.
And I'm Gary Jordan with NASA Communications. This mission is one of the first under a task order with NASA's Commercial Lunar Payload Services Initiative. Under Artemis, we're returning to the moon to conduct groundbreaking scientific discoveries and technological advancements. And this mission with Intuitive Machines is helping us to get there.
And Gary and I are at Intuitive Machines' facility here in Houston, just down the street from NASA's Johnson Space Center. Right now, inside Nova Control, flight controllers are monitoring our Nova-C class lunar lander named Odysseus ahead of its autonomous landing sequence that begins with powered descent initiation at 5:11 p.m. Central Time for a landing time at 5:24 p.m. Central. Right now, they're keeping an eye on the room's situational awareness tool called the Viz, which you can see on your screen now. The Viz is casted onto a large television in the front of Mission Control, so the activity director and the mission director can have the best view, Gary.
And the Viz is an animation representing real-time telemetry data feeding into Nova Control. Nova Control receives the data, runs it through Unreal Engine 5, and generates a visualization of the data. It's a useful tool for situational awareness and keeping track of what flight controllers expect Nova-C is doing in space. The white line points to the moon. The blue line is the past and intended trajectory. The yellow and red lines are pointing towards the sun and Earth, respectively. The different color cones you see at the top are the antenna arrays used for line-of-sight communication back to Earth. We'll show the viz periodically throughout our coverage, up to about 12 minutes prior to landing. In these final moments before landing, the most reliable spacecraft data will be relayed through Nova Control audio loops.
And we're starting our coverage later than expected today as flight controllers continue to assess Nova-C's trajectory, guidance, navigation, and control. Nova-C maintained a low lunar orbit, but is in a slightly more elliptical shape. Last night, flight controllers performed a lunar correction maneuver burn to adjust the lander's orbit. This burn kept Nova-C on a trajectory to land in Malapert A, but moved our landing time estimates earlier by about an hour. Then today, flight controllers chose to exercise an additional orbit before starting the IM-1 mission landing sequence. This decision brought us to now, projecting a landing time of 1724 Central Time. Intuitive Machines made the decision to reassign the primary navigation sensors from Odysseus's laser range finding system to use the sensors on NASA's navigation Doppler LiDAR.
This is a dynamic situation, and we'll update you later in the broadcast. Intuitive Machines still intends to land in the optimum lighting window, and the lunar correction maneuver performed last night eliminated the need for the planned 10-second deorbit initiation burn, which would have brought Nova-C from low lunar orbit into the descent phase. Nova-C's current trajectory has it continuing to decrease its altitude over the next hour until the braking burn called powered descent initiation.
Again, the landing time is expected at 5:24 p.m. Central Standard Time, 6:24 p.m. Eastern. The countdown clock at the top of your screen is counting down to the time that we expect to remove, and we expect to remove the countdown clock approximately 2 minutes before the landing opportunity. Getting to this moment, Gary, has been quite the journey, and it's lasted about 7 days so far since liftoff from Launch Complex 39A at NASA's Kennedy Space Center. Odysseus lifted off at 1:05 a.m. Eastern Standard Time from atop a SpaceX Falcon 9 rocket on February 15th. Approximately 48 minutes later, Intuitive Machines' Nova-C class lunar lander entered a translunar orbit, a direct shot at the moon. In the following days after launch, flight controllers in Nova Control commanded engine firings to place the lander into low lunar orbit approximately 100 kilometers or 62 miles above the lunar surface. The journey to low lunar orbit included firing the first liquid methane and liquid oxygen engine in space. This was called the commissioning maneuver. It was a full-thrust main stage engine burn with a throttle-down profile necessary to land on the moon. Over the last 24 hours, Odysseus has maintained its trajectory in low lunar orbit, waiting for suitable lighting conditions to begin its autonomous descent to Malapert A, the designated landing site for the IM-1 mission near the south pole of the moon.
Our joint coverage will follow Odysseus through its descent and landing on the lunar surface, carrying 12 payloads down with it. The mission is enabled under a task order with NASA's Commercial Lunar Payload Services, or CLPS. Here's more on this initiative under Artemis.
Our moon. It seems so close in the night sky, but getting there is really hard. But what if there was a way to change that? Only a few nations have successfully landed on the moon. As NASA sends astronauts back to the lunar surface, this time to stay, we will need to send science and technology instruments ahead of time to lay the foundation for human exploration. To make this happen, NASA is helping establish a commercial lunar economy. For the first time ever, there will be commercial delivery services to the moon. We are enabling American companies to send our payloads to the lunar surface for us. These delivery services will expand our capabilities for exploration, radically increasing the amount of science we can achieve. This high-risk, high-reward initiative will invest in and leverage the entrepreneurial spirit of American innovation to launch a commercial lunar marketplace, advancing technology and exploration for all of us. With this never-before-seen streamlined access to the moon, we will be able to make novel measurements and develop technologies that scientists have long wanted to do on the lunar surface. And as this new industry matures, this commercial delivery service for NASA and other customers could expand beyond the moon to other destinations in our solar system. And we can learn to live on another world because we are explorers.
CLPS is an important pathway towards long-term exploration of the moon and part of NASA's Artemis missions that will establish a sustainable presence in the lunar vicinity and prepare humans for missions to Mars. For more on how this fits in with the greater plan, let's head over to NASA's Leah Cheshire, who's just down the hall. Hey, Leah.
Thanks, Gary. I'm here with Joel Kearns, NASA's Deputy Associate Administrator for Exploration. Thanks so much for being here, Joel.
Oh, thank you, Leah. It's great to be here on Landing Day, which is the culmination of about 5 years of work by Intuitive Machines Corporation.
Yeah, we're really excited, and we want to know a little bit more about NASA's goals for the CLPS initiative.
Okay. So, most basically what we want to do is we want to have American companies take NASA equipment and scientific investigations all the way to the surface of the moon and not have to have NASA do that ourselves. NASA is really good at doing robotic space science missions, whether that's the James Webb Space Telescope or it's the Mars rovers. But when we knew about 5 or 6 years ago that we would start going to the moon to do science and exploration investigations, we knew we'd be going back every year, so we turned to industry to see if they could actually take us to the moon instead of us having to do it ourselves. And that's how we came up with commercial lunar payload services. There's 3 objectives for commercial lunar payload services, or CLPS. One is that we want to do great science on the moon. The second is we want to test out technology and engineering for future human exploration in Artemis. And the third is we want to generate a group of companies that are highly skilled in doing these robotic lunar landings so that we can use them as part of our Artemis initiative.
Well, let's talk about that a little bit more. How is CLPS beneficial to the Artemis campaign?
Well, a number of different ways. For example, we will do science at the South Pole with our astronauts in Artemis and also with robotic explorers. They'll be brought down on CLPS. But we're also going to use these robotic landings, these commercial robotic landings, to do science at places where we won't initially send astronauts. We can use them, for example, this Intuitive Machine mission that's going on today that'll land in the South Pole region will be one of the first forays into the South Pole to actually look at the environmental conditions to a place we're going to be sending our astronauts in the future. That is, what type of dust or dirt is there? How hot or cold does it get? What's the radiation environment? These are all things you'd really like to know before you send the first human explorers. I'd also say that in the future, when we are flying humans to the moon as part of Artemis, we can use commercial services like CLPS to pre-stage equipment or other cargo so that it's there waiting for the astronaut explorers when they land.
And this is an entirely new approach that uses a privately developed lunar lander. What are some of the most important takeaways on risks but also benefits of a model like this?
So when industry came to NASA about 6 years ago and said, we could do this for you as a service, what they said was they thought it would be less expensive than if we did it ourselves, that they could do it faster than we could set up to do it, and that they could do it more frequently, that they could do more than one mission, every year or two. And so far we've seen is that looks like that's going to be true. What we're waiting to see, such as with the mission today, is can they actually do this incredibly difficult thing? Can they really land on the surface of the moon robotically? This is something which is extremely challenging and difficult to do. The moon has no air. You can't use parachutes or wings to slow down. You have to, in effect, ride a rocket engine all the way from orbital speed, thousands of miles per hour, all the way down to a very soft touchdown speed to land in this place, which is very rough, pretty rugged, in really unusual lighting and communication conditions. So this is not an easy thing we have asked these companies to do, but if they're successful, the upside for American exploration is just so great, we have to try it.
Yeah, absolutely. Those are important distinctions. And thank you so much for joining us here today, Joel. With that, we're going to toss it back to Josh and Gary to preview the landing sequence.
Thanks, Leah. We're following along with Nova-C's descent toward the lunar surface. The lander is continuing to decrease its altitude until the powered descent initiation, an 11-minute braking burn that sets Nova-C up for the final moments prior to touchdown. That time of ignition for PDI, or powered descent initiation, is 5:11 p.m. Central Time, 6:11 p.m. Eastern. The entire landing sequence is autonomous, meaning the lander is in control of every milestone required for a lunar landing opportunity, Gary.
And completing a soft touchdown comes with challenges unique to, say, landing on the Earth or Mars, because there's no atmosphere.
Gary, it's an entirely different playbook as we've seen this dynamic situation play out today. Let's take a look at the IM-1 mission's complete trajectory approach as of launch. The Intuitive Machines IM-1 mission is sending commercial and NASA payloads to the lunar South Pole region on an uncrewed robotic Nova C-class lunar lander called Odysseus.
The lander is the tip of the iceberg, and what's below that is the full program that is on a miniature scale, very similar to what the Apollo program had.
The IM-1 flight path mirrors the historical achievements of Apollo 2, starting with separation for the launch vehicle on a direct shot at the moon.
That trajectory is basically like throwing a fastball that is going to hit the moon 6 or 7 days later, like an outfielder stretching out to grab it.
The first 4 days are dedicated to flight controllers in Houston firing the lander's 3D printed liquid methane and liquid oxygen engine to make small course adjustments to hit its orbit target around the moon. This particular coordinate system is called the B-plane.
You can think about the B-plane kind of like the backboard of a basketball ball. And you basically know when you shoot hoops that if you can get the basketball in the square on that backboard, it's going to go in. And the B-plane for astrodynamicists is very much the same thing.
With the B-plane on target, Odysseus is prepped for a critical autonomous maneuver on the moon's far side. This critical burn maneuver is completed in the blind, with the moon blocking direct communications back to Nova Control in Houston.
Once we get around the moon, we have on the day side of the moon, the sun heating us from one side and reflected infrared light off the bright moon warming us on the other. Then we plunge into night, and now we're cold on both sides. It's very tough.
About an hour before landing, flight controllers command Descent Orbit Insertion, or DOI. This is a main engine firing to slow the spacecraft so its altitude drops from 100 kilometers to about 10 kilometers above the lunar surface. After DOI, Odysseus coasts for about an hour before starting its final approach.
And then we reach a point called powered descent initiation. The guidance system on board makes the decision to activate the main engine at very close to full power.
Cameras and lasers are feeding information to the lander's navigation algorithms, which provide guidance, navigation, and control. With a safe site identified, Odysseus enters a 3 meter per second descent, then down to 1 meter per second for the last 10 meters to the lunar surface. Now, the lander is using an inertial measurement unit, which is similar to a human inner ear that senses rotation and acceleration. Flight controllers expect about a 15-second delay before confirming the ultimate milestone, softly landing on the surface of the moon.
And I can tell you just from doing our simulations, that's the longest 15 seconds you'll ever experience as you wait for the final light to turn green to indicate that you've landed on the moon.
Approximately 12 minutes before our landing opportunity, we are going to show this animation of the landing sequence to describe the lander's autonomous operations, starting with powered descent initiation, or PDI. During this maneuver, Odysseus must reduce its velocity by approximately 1,800 meters per second. You can think of it as a braking phase. Then, the lander pitches upright using its main engine with the Hazard Relative Navigation, or HRN, now being fed by NASA's NDL sensors, facing toward the area where the lander intends to touch down. At this point, HRN will autonomously scan the intended landing site for a safe landing area. Then, the lander's guidance, navigation, and control system commands Odysseus to a point approximately 30 meters above the designated landing site, and the lander goes into a vertical descent followed by terminal descent. Intuitive Machines created Nova C for the CLPS initiative and commercial enterprise with the goal of creating a lunar economy.
And Nova C is Intuitive Machines' first autonomous spacecraft. Nova stands for new, and C is the Roman numeral for 100, the lander's approximate payload capacity. With that, let's learn more about the Nova C-class lunar lander.
This IM-1 mission lander is named Odysseus. The name was nominated by Assembly, Integration, and Test Engineer Mario Romero after the Odyssey and its epic voyage across the daunting, wine-dark sea. Including landing gear, Odysseus is 4.6 meters wide, and with its top-deck solar array, it's 4.3 meters in height. It's a taller design that accommodates payloads and the lunar South Pole lighting conditions. Its hull diameter is 1.6 meters, with payloads affixed to the entire exterior of the lander, making its total payload capacity approximately 130 kilograms. The lander weighs 675 kilograms, but packs on weight when loaded with fuel. Odysseus uses composite helium tanks to pressurize its liquid methane and liquid oxygen main engine that can throttle down to perform its final descent to the lunar surface in one continuous burn.
Intuitive Machines' IM-1 mission is supported by NASA's Commercial Lunar Payload Services Initiative, which allows rapid acquisition of lunar delivery services from American companies. The instruments on board advance capabilities for science, exploration, and the commercial development of the moon. Commercial companies were challenged to come up with their own way to design and fabricate a lunar lander and conduct operations. For this commercial mission, Intuitive Machines elected to support the communications between the spacecraft and Nova Control through its own private ground-based network. And it's not the first time Intuitive Machines used this network in deep space.
Well, that's right, Gary. NASA worked with Intuitive Machines to perform technology demonstration of this capability on NASA's Artemis 1 mission, which helped us verify the network for operational use during this CLPS mission. The Lunar Data Network, or LDN, uses ground-based networks to communicate into deep space, so we could lose signal while Nova C is on the far side of the moon. However, the trajectory of the lander's low lunar orbit does allow for near continuous line of sight with Earth and ground station coverage. Let's head over to NASA's Leah Cheshire to learn more about this network. Leah.
Thanks so much, and I am here now with Trent Martin, the Intuitive Machines Senior Vice President of Space Systems. Thanks for joining us, Trent.
Thanks.
We're here to talk a little bit about the Lunar Data Network. This is a private deep space network, belongs to Intuitive Machines. How does it differ to have this commercially available space network, and how is that different from NASA's Deep Space Network?
So when we first got onto the Commercial Lunar Payload Services contract, we were trying to find a way that we could get our data from our landers back to the Earth. We were worried that the Deep Space Network, which is often oversubscribed, particularly with James Webb Space Telescope now, that we would have limited time. So what we did was we created a network of large dishes across the planet that allow us to take our data from the moon and deliver it down to the Earth.
And we initially tested this out during the Artemis 1 mission. So how did Intuitive Machines work that out?
Yes, we worked a reimbursable Space Act agreement with NASA to allow us to test our network not only with Artemis at 430,000 kilometers, but also with the Lunar Reconnaissance Orbiter, as well as the GOES satellite.
Okay, and what are the goals overall for Intuitive Machines? How do you want to expand this LDN coverage?
So we believe that as the market expands at lunar distance, many people will need the capability to send data back, particularly if you're operating spacecraft on the backside of the moon. You need to be able to have a relay satellite. So we're going to put relay satellites in orbit to complement our ground-based systems, which are, again, large dishes all over the world. And by doing that, we'll be able to hopefully create a market for that data system from lunar space.
Okay. Is there anything else that you want to share that has gone into the development of this network?
It's really exciting. We've actually been using it this week once we launched Odysseus into space, and we're taking it to the moon. We've been using this network that we tested with NASA systems for the whole week, and it's been incredible to see it work and see it in action. We have a long ways to go with it. We need to add additional satellites to the system so that we can relay data back from the moon. But we think it is the future of humanity in lunar space.
Thanks so much. It's really exciting to see this in action. And we are just minutes away from acquisition of signal to confirm deorbit insertion. So we're going to send it back over to Josh and Gary to follow along with the operations.
Thanks, Leah. That Lunar Data Network information feeds into Nova Control's communications and ground network console screens. It's just one of many different screens that are used by the flight controllers, and we want to bring you closer into the mission and into our Mission Operations Center. Let's take a look at what flight controller teams are seeing now. This particular screen is called the Deorbit Descent and Landing, or DDL screen. This screen is primarily used by the mission director and landing system experts. It's used primarily while Nova C orbits the moon and through landing. The top right images of the moon are called the lunar tactical view. When the dots turn red, the lander is on the far side of the moon, and green is on the near side. The line is the tail where Nova C is, with each dot representing 10 minutes of elapsed time. The acceleration sensor advanced portion of the screen shows raw acceleration values from Nova-C's inertial measurement unit. This is used a lot during burn maneuvers and is a more robust way of measuring acceleration over time with the ability to look back at what has happened. For some reason, flight controllers have lost data. Finally, the column on the right is a received, accepted, edited, and failed pre-checked, or RAFE chart for short. When each of these lines are on top of each other, that's a good indication that Nova-C's navigation system is in good health. That's because every measurement Nova-C makes must be received, accepted, edited, or failed pre-check. The failure is a possible outlier of data that the lander's computer automatically knows is bad information. Collectively, the DDL screen is one of many data displays that flight controllers are monitoring to successfully navigate Nova-C to the lunar surface.
Data visualization is an essential component for flight controllers who need to process this data for real-time decision-making in Nova Control. Now again, we're following along with the flight control teams here in Nova Control prior to the next critical steps, including activation of the navigation Doppler LiDAR to provide guidance, navigation, and control for the landing phase. This is expected around 4:45 p.m. Central Time. The next critical milestone is powered descent initiation at 5:11 p.m. Central. This burn is the first in a sequence of maneuvers that starts about 12 minutes prior to landing, or about 50 minutes from now. Nova-C is, of course, landing on the moon as a delivery truck for the scientific instruments and technology demonstrations on board. There are 12 total payloads, 6 of which are NASA's. Let's review a few of those payloads as we continue to descend towards the lunar surface. First is radio observations of the lunar surface photoelectron sheath, or ROLSes. ROLSes will employ 4 antennas and a low-frequency radio receiver system to determine the density and scale height of the moon's photoelectron sheath, a very thin layer of electrons above the surface of the moon, and will also detect solar radio bursts, radio emissions from Jupiter, dust impacting the surface of the moon, and how radio noisy Earth is.
An exciting radio telescope is going to be placed on the moon. It is called ROLSes. It stands for radio wave observations from the lunar surface of the photoelectron sheath. It's going to detect all kinds of radio emission that is falling on the moon. Right now it is close to solar maximum, so the sun is producing a lot of coronal mass ejections and radio emission associated with them, and we can detect these radio bursts from the sun. Characterization of the radio environment of the moon is very important. It has not been completely done, and therefore ROLSes will be able to contribute in identifying various sources of radio emission on the sun. If you're setting up an observatory on the moon, we should know what kind of radio interference we get there.
The Laser Retroreflector Array, or LRA, is a collection of 8 retroreflectors that enable precision laser ranging, which is a measurement of the distance between the orbiting or landing spacecraft to the reflector on the lander. LRA is a passive optical instrument that will function as a permanent location marker on the moon for decades to come.
This is a little mirror that's aiming at you all the time, regardless which way you're looking at it. My name is Xiaoli Sang. I'm a LiDAR instrument scientist. It's a small retroreflector mounted on aluminum shell on the intuitive machine landers. When you shine laser on it, it reflects right back at you. The purpose is to have a precise fiducial marker on the landers. It serves as a landmark for future missions if you want to go back and land it there.
Stereo cameras for lunar plume surface studies, or SCALPS, will use a suite of 4 cameras to capture stereo and still image data of the dust plume created by the lander's engine from when it begins its descent to the lunar surface all the way down through engine shutoff.
SCALPS is an array of small cameras that will be placed around the base of a lunar lander and collect imagery during the descent and landing of the vehicle. Using a technique called stereophotogrammetry, we can use those images to reconstruct a 3D shape of the ground. As the lander comes down, its hot engine plumes will interact with the surface. Our cameras will begin acquiring images from before this interaction begins until after the vehicle has landed on the surface. The SCALPS cameras will specifically be looking at the overall crater formation and erosion of the ground due to the rocket plumes. The final stereo images, which will be stored on a small onboard data storage unit, will be transferred to the lander and then downlinked to Earth, where we can use them to reconstruct the overall erosion volume and shape of the ground. With the Artemis program, we plan to establish a sustained lunar exploration and try to land multiple payloads in close proximity to one another. SCALP's data will be a critical part of understanding these phenomena and improving our computational models to inform these future landings.
Radio frequency mass gauge, or RFMG, is a fuel gauge used to measure the amount of propellant in spacecraft tanks in a low-gravity space environment. Using sensor technology, RFMG will measure the amount or mass of cryogenic propellant in Nova-C's fuel and oxidizer tanks, providing data that can help predict fuel usage on future missions.
I'm Greg Zimmerly, the principal investigator for the Radio Frequency Mass Gauge Payload. This instrument is a space-age fuel gauge. We're going to use it to measure the amount of cryogenic propellant in the Intuitive Machines Nova-C lander propellant tanks. These propellants are very cold. They're at about -300 degrees Fahrenheit. Now we're integrating the instrument onto an actual lunar lander. Future lunar missions, like those in the Artemis program, will likely also use cryogenic propellants and have to store those propellants in space for long periods of time. So having an instrument like this that can measure the propellant in the tanks in low gravity will help future lunar missions know how much fuel is in the tank at all times.
Now we'll discuss two more NASA payloads, Navigation Doppler LiDAR, or NDL, and the Lunar Node 1, or LN1, later during our broadcast. We'll have a special guest later in the broadcast to talk NDL upon its activation during descent. And Josh, we did get word that some of the processing of the optical images from NDL are already performing. They did some checks, and they're performing very well. Now, a common theme you'll find among the NASA payloads on IM-1 is helping to demonstrate technologies and our understanding of the lunar landscape that could very well improve operations for landing on the moon in the future. From understanding the environment to precision sensors to literal beacons, the technology on IM-1 will help guide technologies and operations for future lunar exploration.
And Gary, with CLPS as a springboard of innovation, Intuitive Machines designed and developed its complete lunar program to help support CLPS and carry out the essential part of that directive, which included calling for the commercial development of the moon. Back in 2018, the U.S. government declared the moon of strategic interest. At that time, few companies and institutions were working on payloads designed for the moon because no one had been to the lunar surface in over 50 years. Gary, in the time it takes to get an undergraduate degree, 6 commercial entities created payloads for the IM-1 mission. We'll view all of them as pioneers helping shape this brand new lunar economy.
And Josh, a true lunar economy should not have just NASA as a sole customer. NASA's CLPS initiative encourages a model where NASA is just one of many customers. And this is an important element to ensure that this model of transporting incredible science and technology instruments to the lunar surface is a sustainable and robust one.
Well, it's important, and Gary, it's also promising in this situation. The commercial interest for delivering science and technology demonstrations continues to grow. As of our 3rd planned mission, we're seeing more and more non-CLPS payloads from both domestic and international companies and institutions, which are driving us towards a future, maybe completely commercial mission to the moon, possibly as soon as our 4th mission.
Well, even on IM-1, there is a variety of unique commercial payloads. It's a good snapshot of out-of-the-box ways to think about what the moon can offer.
Well, that's part of the challenge. Beyond just creating the capability to land on the moon safely, we had to look toward a new emerging ideas and find innovative ways that may add value on Earth and spaceflight. Let's learn a little bit more about those payloads and the lunar lander attempting to make history.
The Nova-C was our version of a liquid oxygen, liquid methane lander, and we went about imagining that into existence.
Intuitive Machines' Nova-C class 3D printed engine took its first breath of liquid methane and liquid oxygen in 2018 on an airstrip at Ellington Airport in Houston, Texas.
We didn't have enough money for a facility with blast walls and water suppression or water deluge. So we had to test outside in the environment of Houston, where the temperature is about 100 degrees and the humidity is like the same. And we have an 18-hour day, rolling out to the runway. It was brutal. But we did it to get the critical test engine data we needed to build our own engine.
Designed, manufactured, and controlled in space by Intuitive Machines, Nova-C's structure is primarily carbon composite.
We needed to build the lightest weight structure we could. That meant honeycomb aluminum core with composite face sheets, composite struts, and most importantly, linerless composite propellant tank. Man, what a challenge that was.
Between the engine, carbon composites, software, and electronics required to build a Nova-C lunar lander, it took an incredible amount of touch labor to get to the launch pad.
We worked very closely with San Jacinto Community College to create a certification course for technicians, where they would take these certifications. We then at Intuitive Machines would give them an internship and test them out in the workplace. And anyone that showed the aptitude to be a really good technician, we hired on the spot.
Nearly all of the lunar lander's payloads are mounted to its exterior, including 6 NASA-provided payloads that will help lay the foundation for Artemis missions. Embry-Riddle Aeronautical University's EagleCam, designed to deploy off Nova-C right before landing to take third-person perspective images. The International Lunar Observatory Association's camera system, mounted at exact angles that could capture images of the Milky Way from the lunar surface. A data center technology demonstration by Lone Star Data Holdings, and Omni Heat Infinity, Columbia Sportswear's thermal reflective insulation used in many of their outdoor products, will help protect Nova-C from extreme temperatures in space.
They've got brilliant ideas, and if we can help facilitate those startups to help build this economy, I think that raises all boats, and it's as serving as the transportation leg to the moon, we're happy to accommodate those kinds of companies.
Now, the lander and our payload customers require command and control in space. Intuitive Machines' Mission Operations Center provides both of those elements. It's called Nova Control, Nova being the name of our lunar lander class, and Control being the nerve center of our entire lunar program. Its unique circular design fosters a collaborative environment where flight controllers and customers may make agile decisions. Let's take a live look.
Yeah, and inside that flight control room, Josh, it's important to note that these are not the only teams that have been in this room over the past 7 days. This is staffed 24/7 inside in Nova Control here. There's red, white, and blue teams that support this mission.
Gary, the mission required 24/7 operations. We're somewhere in between the 7th and 8th day. This has been 3 teams, red, white, and blue, working 8-hour shifts, which really turned into just about everybody working 12-hour shifts each. In addition, there's another team, the gold team, that's running problems and solving solutions that are coming up in the future. And at this moment, we talked about this being a dynamic situation, using 2 of NDL's lasers to feed into our HRN and TRN cameras to provide a landing solution. Every asset available out of all of these teams is on hand right now to solve these intractable problems and take the best shot at the moon we possibly can.
It really took a team to solve some of these, as you mentioned, a dynamic situation. Now, you talked about the design of this room, fostering that collaboration. It's a little different from what I'm used to over at the International Space Station Flight Control Room, where you have consoles that are facing towards large screens. What exactly is the logic behind this particular design?
Really, we wanted to get everybody together into where we're a small company. There's not a lot of us. Agility is our strong suit in this situation, and this room really suited us. It's a situation where we can put our payload customers inside the center, or let's say we need to bring in operators who have knowledge of the things that need to happen in the future that we haven't quite touched on as a team, but you can insert those folks into the center of this room, make quick decisions, respond to problems, and that's really the way that we see tackling some of the hardest challenges in the world, and certainly right now for us, this is one of the hardest challenges on the moon, most certainly.
Which we are saying absolutely, and it takes takes everybody in this room, and everyone has their respective roles, just like we see with any spacecraft. Each of these individuals provides insights into a specific spacecraft subsystem.
And the captain of this whole thing is usually the mission director. In this case, this is Blue Team. That is Dr. Tim Crane. He's our co-founder and chief technology officer, serving as mission director today. Flight control operators continue to monitor Nova-C's performance. Operationally, we're still counting down to PDI ignition at 5:11 p.m. Central Time and landing at Malapert A at 5:24 p.m. near the south pole of the moon. For more on Malapert A, let's head over to Leah Cheshire. Leah?
Thanks so much, and I am now here with Ben Bussey, Intuitive Machines Chief Scientist, to talk about Malapert A. Thank you so much for joining us, Ben.
It's great to be here.
Now tell me a little bit about this landing site. Why was it chosen? What sets it apart?
So the most important factor when selecting the landing site was to find a good, safe site for Odysseus to land. And we're landing in highland terrain near the poles, and that was a fun challenge for the team. But we think we found a good, large, safe area free of boulders and craters. The other key factor was to try and land in the south polar region of the moon. If you know, NASA, through the Artemis program with their international partners, will be sending humans to the moon in this decade. So the goal was to find somewhere in the south polar region that was large and safe, and we sort of think just outside the rim of Malapert is sort of a Goldilocks location that will allow all the payloads to get the data that they want to get.
And you talked for just a second about that lunar highland material. That's what we believe Malapert A to be composed of. What is really interesting about the lunar highlands?
So if you look at the moon, you will see bright and dark regions, and the dark regions are lunar mare, which are old volcanic flows. The bright regions are mountains, are the highlands, which actually represent the original 4.5 billion year crust of the moon. So they're scientifically very interesting. They're also the same geology that the crew will visit. And so we want to go and get the first data of the highlands near the poles. And so we have one of our instruments, for example, is SCALPS, and NASA likes its acronym. So it's the stereo camera for lunar plume studies. And so that camera, which is 4 video cameras, will image the dust of the highland terrain right before we land. And so we will learn how it behaves as landers come down. So as we start to put multiple things near the poles, we know how far away we have to land.
And we know that there are some interesting conditions for these areas in the lunar South Pole. That can be lighting, that can be communications, terrain itself. So what can we expect at Malapert A?
So yeah, as you get very close to the poles, the lighting and communications becomes very challenging. And so for IM-1, we've gone to about 10 degrees, about 300 kilometers from the pole. And we think that's a good location because it's the closest to the pole that anyone's landed. But for example, we've chosen a site where you can see the Earth all the time, which is obviously communications being a key challenge. Whereas for IM-2, our second mission later this year, we'll go even closer to the pole. So for example, one of the things that we can study is, while we see the Earth all the time, it's still close to the horizon. And one of the things that communication engineers want to know is how communication is affected when the Earth is really close. So that's one example of something we can do in support of Artemis.
Well, thank you so much for joining us here today, Ben. That's all the time we have right now. We're going to send it back to Josh and Gary to talk a little bit about the landing sequence.
Thanks, Leah. Yeah, Malapert A is a fascinating satellite crater to Malapert, a crater only 300 kilometers from the moon's south pole. The site is named after Charles Malapert, a 17th century Belgian astronomer. The area around the landing site is believed to be made of lunar highland material, similar to Apollo 16's landing site. Apollo 16 was the first Apollo mission to visit the lunar highlands in an area called Descartes. Scientists believe the highlands offered insights into the moon's early history. The Descartes landing site turned out to be a source of rich scientific information. A large sample of rock called anorthosite was recovered from Descartes, which solidified more than 4 billion years ago during the moon's formation, when the outer regions were still molten. The IM-1 mission is carrying NASA payloads that may help better characterize this important scientific landing site for future Artemis missions.
And Gary, we were originally targeting from NASA Oceanus Procellarum. It was a lunar mare in the region of the near side of the moon. The decision to move from the original landing site in Oceanus Procellarum was based on the need to learn more about terrain communications near the lunar South Pole, which is expected to be made up of some of the best locations for sustained human presence on the moon. Landing near Malapert A also will help mission planners understand how to communicate and send data back to Earth from a location that is low on the lunar horizon.
Now we're coming up on the NDL activation. We have more information about how Intuitive Machines flight controllers intend to land on the moon using this NDL, NASA's Navigation Doppler LiDAR.
And Gary, since choosing to orbit the moon one more time, flight controllers have been working to resolve a challenge with the lander's laser rangefinders assigned to the terrain relative navigation and hazard relative navigation cameras. Those provide landing solutions to Odysseus. The lasers are intended to determine altitude and horizontal velocity, but the ones on the lander right now are not working.
These are essential measurements required to land on the moon. And while Nova-C's laser rangefinders are not operable, NASA's Navigation Doppler LiDAR sensors are.
So during the last 2-hour orbit, flight controllers have been loading software patches and resetting the lander's guidance, navigation, and control system to use 2 laser beams from NASA's Navigation Doppler LiDAR as primary navigation sensors to land Odysseus.
That's right, and we're coming up on the timeline for when Nova-C is about to begin the activation of NDL. This is a 3-step process, from powering on, becoming ready for operation about 5 minutes later, and then integrating those sensors with Nova-C's terrain and hazard relative navigation cameras ahead of Nova-C landing. So while we wait, let's learn a little more about NDL.
So the Artemis program is taking NASA back to the moon, and everything that goes there, including the instruments and people, must be flown there safely and landed there precisely. So the landing phase of that task is one of the most critical aspects of it. NDL is a LiDAR instrument that is used to enable that capability. It uses light in the same way that sonar uses sound. For NDL, we have 3 telescopes where light would come out of the telescope, hit the moon's surface, and some of that light will be reflected back. These telescopes are mounted on the outside of a vehicle so you get a clear view of the ground as it's coming in for a landing. In the Apollo era, large radars or astronauts using their eyes looking out of a viewport were used to help land the vehicles. NDL is going to have to take the burden off of the crew with a much smaller, lower power, and more accurate instrument.
And we just got an update from one of the flight controllers that the HRN and TRN cameras assigned to Nova-C are still nominally processing images using 2 of those NDL lasers. Quite the feat, Gary.
No, it's absolutely incredible and a very important milestone to reach. Now, with that understanding, let's learn more about how this technology is playing an active role in this dynamic situation. Let's head over to Leah Cheshire. Leah?
Thanks so much, Gary. I'm joined now by Prasanth Desai. He's NASA's Deputy Associate Administrator for the Space Technology Mission Directorate. Thank you so much for being here.
Grateful to be here.
So let's talk a little bit about the novel landing technology that is NDL. Can you explain that to us?
Yeah, so NDL stands for Navigation Doppler LiDAR. And one of the challenges for doing any space missions is knowing where you are and trying to figure that out, right? And so we're looking to develop newer and newer capabilities that we can do that more precisely and that take up less volume and mass on the spacecraft so that you can have all the available payload mass for instruments and other scientific things we're trying to do. And so this is the next generation of a new capability where we're trying to go from the traditional measurement using radar to a laser-based system. And so that's what this Navigation Doppler LiDAR will be doing, is sending out 3 laser beams to try to get the velocity measurements in the lateral direction as well as the vertical direction.
So when it comes to NDL, what are some of the challenges we expect to see when using this technology?
So we've tested it on the ground in a number of platforms, from helicopters to landers here on the surface, on the Earth, to test this out. But this is the first time we're going to test it actually in the space environment on a lunar surface, right? And so we will see how that different environment will really affect the systems, right? And so one of the things that we would really like to know is what how the pulse comes back after they send the laser, and how it reflects back to the system, how long it takes to process, and how it will help define the solution to figure out the trajectory to go down to landing on the surface.
Now, this technology has become a little more critical for today's mission, so can you talk about how NDL is now being used in today's landing?
Right, so we put this as a tech demo with tech demonstration as a test. Right, we weren't planning to use it in line with the actual mission coming down to the landing, but now we are. So basically, it is now the primary system to help provide the velocity and altitude information so that the lander can land safely on the surface. And that's important because as the lander comes close down, we don't want it to tip over. And so we need to get an understanding of the vertical velocity so it knows how much thrust to slow down, but also the lateral velocity, because if it comes down sideways too much, it can tip over and fall. So by knowing the velocity, the lander can decide exactly how to come down and hover, basically slowly to come down, and that's why it's really important to do this testing. But here we are today, we're going to try it for the first time in line, and so we're very excited for the mission.
Yeah, a demonstration totally in action.
Yes.
So just very briefly, there are 2 other tech demos on this mission. Can you cover those very quickly?
Yeah, so 2 other things that we're trying to improve on is one, radio frequency mass gauge, which is to try to get a measurement of the fuel that's on any system, any spacecraft. One of the things about low gravity is the propellant doesn't settle down, where like in a car gas tank, it's on the bottom so you can measure it easy. In space, it floats. And so how can we do that so we know how much propellant there really is? And then the other one is scalps. One of the things that as it lands, the thrust is going to throw up all this ejecta of the lunar regolith and thing. And so we have 4 stereo cameras that are going to take images of that and get data so that we can improve our modeling, so that in future landings we can make them more safer and things like that. So we're using that as a technology demonstration as well to improve future landings to make them more safer.
Well, thank you so much, Prasanth. It's really been great speaking with you, really exciting stuff. And for now, we're going to send it back to Gary and Josh.
Hey, thanks, Leah. Nova C is a little less than 55 kilometers from the lunar surface and about 20 minutes to powered descent initiation, a critical maneuver that marks the beginning of Nova C's final moments before touching down on the lunar surface. It's no secret that landing on the moon is challenging. Countries around the world have attempted this incredible feat, some successful and some not. Of course, the United States has landed on the moon many times, most notably during the Apollo program. But this may be the first landing by a U.S. commercial company enabled under NASA's CLPS initiative. Ahead of these important milestones, let's discuss the challenges of landing on the moon through CLPS. Take a look.
Landing on the moon is hard. We're going back. Under this Artemis program, we're going to be sending humans to the moon for the first time since Apollo. So ahead of humans, we want to get up as much science exploration and technology experiments as possible.
So CLPS starts facilitating a lot of the early science, the things we want to learn before we even send humans. CLPS stands for Commercial Lunar Payload Services, CLPS.
The services part is the key element. Ordinarily, when NASA delivers a payload to the surface of the moon, they do it with a commercial partner, but NASA controls the building of the vehicle. Now, we're buying the service of delivery of our lunar payloads to the surface of the moon.
It is a delivery service, akin to a delivery service that you'd have here on Earth.
NASA will provide payloads to a commercial company. They decide how to get it to the moon. They have to develop their own lander, but they also have to manage the entire end-to-end mission.
It's meant to provide affordable, rapid, frequent access to the lunar surface through American companies.
We're funding different companies.
We have commercial companies that are competing to win task orders to deliver our payloads to the surface of the moon.
One of the goals when we started CLPS was to help establish a lunar economy.
Somebody has to do it first, and then it becomes commercially available. Then they're able to crank them up. Then they're able to make it more affordable. And so the lunar surface is just the next frontier for a commercial environment.
But we had to acknowledge up front, all the way through the highest levels of the agency leadership, that some of them will fail. These missions may not be as successful as a traditional NASA mission.
We have accepted the risk that going through this innovative approach with these commercial companies, that there could be some failures. Some of them are new companies. None of them have ever successfully landed on the surface of the moon. So they're going to learn lessons.
We need to give our vendors the opportunity to learn.
And so that'll help ultimately buy down our risk as these companies learn, okay, what does it take to actually build up the lunar lander, integrate payloads, get to the lunar surface and land safely.
They've been able to demonstrate that they have very, very good technical depth and the ability to design and execute missions. We're willing to take more shots on goal. And we aren't risking human lives. And in the big picture, if we're flying missions at 1/10 of the cost of a NASA mission and we fail 2 of them, we still get 8 missions for that same price.
Even with 1 or 2 or 3 failures, this is still a very economical proposition. It's a risk posture which is more risk tolerant than NASA is accustomed to. There's not a single one of these companies that's willing to bet their mission on a coin toss. Every one of them is doing what they can in order to have the most successful mission possible. But the important thing to realize is that risk tolerant does not mean risky. And the rewards are a long-term ability to get payloads to the moon inexpensively, frequently, and rapidly.
We want science, so we can then put more of our resources on even more science, exploration, and technology payloads and get more of a return on investment when we get to the moon.
CLPS provides tremendous benefit across the scientific and economic communities.
So there's a lot we'd like to learn about the moon to help human habitation and prepare us for missions to Mars and beyond.
So the moon is the first step.
The teams here in Nova Control have been working diligently over the past 7 days to take us this far and are laser focused on the operations ahead. We're following the clock down to the start of those autonomous operations of Nova-C, starting with the powered descent initiation. For now, we're heading back over to Leah Cheshire, who's standing by with NASA's Associate Administrator. Leah.
Thank you, Gary. I'm joined now by Jim Free, NASA's Associate Administrator. Thank you for joining us, Jim.
Thanks for having me.
This is a big day, and what are some of the challenges to landing on the moon that people might not expect?
Well, it is a big day, by the way. You're right. I think the challenges are multifaceted. First, getting into lunar orbit is a challenge. Going to the South Pole is different than going to other parts of the lunar surface. The lighting conditions are a lot different than at the equator. So you have your hazard detection has to be a little more reliable. You have to be able to do that last minute avoiding of the hazards that are on the surface and finding that right place to set down so you're also level or within a tolerance that you can be for level on the surface.
We've talked a little bit about how this is a different model for us. So how does NASA help ensure success while we also allow these companies to figure out their solutions?
We're able to offer our technical expertise, so companies can ask for technical experts from NASA that might be an expert on lunar surface conditions or orbits around the moon, or even just in assembly of the spacecraft, the vehicles. But they can also ask for help during the mission. We provide help through our deep space network to get the communications, to bring the data back to the control center here to help them maybe understand their orbit better or get more communication with the spacecraft as well. So both in advance of the mission and during the mission also.
And CLPS is just one way that NASA is using, we're working to strengthen the American space economy. So what are some other ways, and why is NASA pursuing this commercial route for complicated space missions?
So we started back in space station, where we started with the commercial cargo, where we spurred on investment in commercial delivery of cargo to space station. That's ported over into our cruise flying commercially. We're doing that on the Artemis program, buying things by service so that we can spur on other investment that allows us to get our resources and use them elsewhere to do other parts of our mission, exploring the moon or beyond.
You talked a little bit about Artemis for a second. So how does CLPS fold into NASA's plans with Artemis and with this Moon to Mars architecture?
I think I could talk about Artemis for hours. But CLPS is absolutely essential for Artemis. It's our first steps of understanding the lunar environment. So the Intuitive Machines lander is going to help us understand how the lunar dust moves as the rocket plume, the exhaust of the rocket hits that dust. We need to understand that because we're going to land even bigger landers with our humans in the future, and we want to land it close to our other elements so we're not blowing that dust everywhere. How does it behave? So that's just one part of it, but it is our first step of understanding that environment that we're going to put our astronauts on the surface.
And of course, we're really, really looking forward to that mission. But for now, thank you so much for joining us here today. We are going to go back to Gary and Josh to highlight some more payloads ahead of the powered descent initiation.
Hey, thanks, Leah. A report at 4:54 p.m. Central Time from the flight control teams shared that Nova C is less than 30 kilometers above the lunar surface and is in the lunar southern hemisphere. We're still on track for PDI at 5:11 p.m. Central Time. Nova C will perform this maneuver to slow the vehicle's descent, then pitch over and scan the landing site for hazards, making any necessary corrections in the final burns to ensure a safe landing. We've highlighted 5 of the 6 NASA payloads so far throughout our broadcast today. Let's talk about the final NASA payload, LN-1. Lunar Node 1, or LN-1, is a small CubeSat-sized flight hardware experiment that integrates navigation and communication functionality for autonomous navigation to support future lunar surface and orbital operations.
Lunar Node 1 is meant to be a demonstration of how we can use various navigation technologies to figure out where you are in and around the moon. I'm holding in my hands the Lunar Node 1 mass simulator. We use this build to test out our vibrational modes, put on a shake table, and also do fit checks with the lander itself. Inside of our payload, we have multiple electronics boards that fit within this chassis that is a little bit about a half a U in size. You can see our external connectors here where we have our data and power to the lander itself. And within here, we have multiple boards that do the power regulation, our data control, our FPGAs, all those kind of electronics pieces are in here, as well as a small S-band radio that attaches up underneath this top radiator in order to distribute this heat, and then to talk to the antenna, which mounts here. This is the same size and build as the flight payload. It's just not covered in MLI or some of the other materials that you'll see on the flight build itself.
LN-1 will test a lunar navigation concept of operations with the implementation of MAPS, or the Multi-Spacecraft Autonomous Positioning System. Ideally, this kind of technology can support a network of communication and navigation amongst local surface and orbital operations. LN-1 will test multiple navigation links from the surface of the Moon back to Earth to characterize both MAPS transfers as well as GPS-like signals that could support a future lunar communication and navigation network.
Gary, one of the best things about communication and data is getting imagery back. And Intuitive Machines has several camera systems on board, including EagleCam. It started as a challenge from our CEO, Steve Artemis, to his alma mater, Embry-Riddle Aeronautical University. Students and faculty created EagleCam to take an out-of-this-world selfie of Odysseus landing on the Moon. The camera system could capture the world's first ever third-person picture of a spacecraft making an extraterrestrial landing. The camera system is designed to deploy off of Nova C approximately 30 meters above the lunar surface and take images of Odysseus during landing. Additionally, the device will test a dust removal system which could lead to the future advances in spacesuit technology. As part of this project for EagleCam, Embry-Riddle teamed up with NASA's Kennedy Space Center to demonstrate the NASA-developed electrodynamic dust shield, or EDS. EDS uses an electric field to remove dust. The technology was tested aboard the International Space Station and will be the first ever demonstration of EDS technology on the lunar surface after landing. Intuitive Machines also had several cameras on the lander, including wide and narrow field of view cameras. They started the mission with incredible imagery as the SpaceX second stage deployed our Nova C lunar lander, capturing iconic images of the Earth after separation. It requires a lot of planning, work, and just a hint of luck. Payload integration managers programmed the lander's wide and narrow field view cameras to take 5 quick images every 5 minutes for 2 hours, starting 100 seconds after separating from SpaceX's second stage. Out of all of those images that were taken, we ended up with just 4 inspiring ones to show humanity's place in the universe. And right now, we're a little more than 10 minutes from powered descent initiation. Let's go to Leah Cheshire one last time for the final interview ahead of this critical maneuver. Leah.
Thanks, Josh. I'm here now with Nikki Fox, NASA's Associate Administrator for the Science Mission Directorate. Thanks so much for joining us.
Thanks for having me. This is a great day.
It is a great day, and you're watching this with leaders from NASA and Intuitive Machines, just very close to here. What's happening in the room right now just before these final descent maneuvers?
Oh, there's just excitement, anticipation. Everybody knows landing on the moon, going to the moon is hard. And we're already celebrating because this mission is already a success. We've launched, we had a beautiful launch. We've taken great science data all the way, every single challenge. The team has really risen up and solved it. And now we're in lunar orbit, minutes away from starting our descent down to the lunar surface. So for me, so many successes with this mission already. So just a lot of excitement.
I'm loving that. So we are working with these American companies in a very unique way. These are challenging goals, and some people would probably consider this a bold endeavor. But what does it mean to you when you look at pursuing challenges in a bold new way?
I mean, you're right. It is bold. It is a new way of doing science. It is a partnership with totally new companies who haven't done these things before, and we are partnering with them, and they are taking our science. It's a way for us to get more science and more technology to the moon quickly. So it's faster. It's very cost-effective. It's very efficient. We're on our way. We've got the 6 payloads from NASA, and we're excited to get them down there. With every new thing we do, there's always a challenge, there's always risks. This is a high risk but super high reward, and it'll get tons of science on the surface. And for my NASA science, this is exciting because our Artemis missions and our lunar science touches all 5 of our science divisions in very profound ways. So super excited.
You said high reward, so I want to talk for a minute about the valuable scientific insight that we can get from the moon. What is that? What does it mean for NASA?
I mean, there's so much we can do on the moon, particularly where this one is going down to the South Pole. We think we're going to find great volatiles down there. So as we get prepared to send our astronauts there, then we know that there's water there, and we can use that water. Water's very heavy to carry, so it's really great if you can use it on the moon. We can break it up into hydrogen and oxygen, use it for fuel. Really great for our sustainability, but also where they're going is one of the oldest regions of the moon, about 3.85 billion years old. So we can actually learn about what our solar system was like before life started. Life is very noisy. We're very, very noisy here on Earth. The moon is just like pristine, and so we can really do some amazing science.
I look forward to learning more about it. So any final words before we wrap it up?
Just thank you. I mean, literally, thank you. This is such an amazing team. Thank you to the people that put the science and the technology experiments on with us, those teams. Thank you to the commercial teams that put their instruments on and are riding with us. Thank you, of course, to Intuitive Machines for this just beautiful, beautiful lander. And thank you to SpaceX for a beautiful ride to space. It's such an incredible effort. All one, I don't know, I'm a big bundle of emotion. Go NASA, go CLPS, go Odie, go Intuitive Machines.
I'm with you all the way. Thank you so much for joining us here today. Now we are following Intuitive Machines flight controllers during Nova-C's final descent. So back to Josh and Gary.
Thanks a lot for that, Leah. During that interview, for folks at home, we did hear that there was a maneuver to burn attitude, which means the lander is starting to make the positional requirements needed. And we're going to start listening into the IM1 channel so folks at home can hear. We just heard from flight controller about 5 minutes until TIG.
Altitude of 10 kilometers, downrange 1,100 kilometers.
TIG being time of ignition, so we're inside of 5 minutes.
TIG minus 5 minute dead pins.
TIG minus 5 minutes. We are standing by for powered descent initiation. Gary, this is a critical 11-minute burn to slow the lateral velocity such that Nova-C can pitch over for further operations. And while we were in that interview, we did hear that the main engine gimbal checkout was completed. So now we're focused on the operations with Nova Control. For folks at home, we are listening in to the live channel there.
That's right. A lot's happening in Nova Control. We're going to be hearing these status calls periodically as we follow the flight control teams that are monitoring Nova-C's descent towards the lunar surface. A lot's happening, Josh. Of course, we have this 11-minute burn. We're focused on the propulsion elements of this PDI. At the same time, the spacecraft is oriented in such a way that it can use a technology called terrain relative navigation to scan the environment along the way. What's happening there?
Right, so we know that we needed terrain relative navigation then when we were descending and coming down to the lunar surface. Now, this involves two pieces. You have a camera and you also have a laser rangefinder. At the top of the show, we started talking about, hey, the laser rangefinder that Intuitive Machines put on Nova-C, it's not operating. We made the decision for flight controllers to utilize 2 of the laser beams from NASA's NDL payload, make the software patches required to reassign those lasers into the TRN and HRN cameras in order to give us an opportunity to land on the south pole of the moon today. Gary, is quite the feat and challenge overcome in just about 2 hours because we elected to delay that orbit and go into another orbit. That's why the show was a little bit later. It appears to be paying out. The last call-outs that we heard, Gary, were talking about beginning processing optical images, and that was nominal. The last time we heard that was just about 20 minutes ago.
The status checkouts of these critical systems are essential to understanding the performance. The folks you see now on your view, this is Nova Control. They're monitoring every step, all the data coming from Nova-C ahead of PDI, which is scheduled just a little bit after 5:11 p.m. Central Time. Exactly what are these folks looking at, Josh?
Well, right now everyone's looking at their assigned screens, and all of them are tailor-made. Generally, there's a few who are looking at the same type of screen, but they're tailor-made for their task. You have Spark looking at electronics, things like how hot are the electronics. Payloads are monitoring different parts and pieces.
5 degrees to burn attitude.
5 degrees left until burn attitude. The vehicle is still getting ready for this PDI ignition, which we expect here in just about 2 minutes, Gary, two minutes. So everyone's looking at their screens and doing their respective jobs and reporting up into the mission director, while the activity director is keeping in touch with everybody and making sure we're putting this whole thing together.
Press started.
There's a call for tank press started. Just a little bit before that, Gary, we did hear that they were working on the cryo fill. So these are all steps that are leading towards PDI, powered descent initiation. We expect that to take about 11 minutes, where we're slowing Nova-C's velocity approximately 1,800 meters per second, and that's required to get this lunar landing opportunity in just a few minutes.
90 seconds to TIG. Propellant tanks at flight pressure.
All right, 90 seconds until we begin that propulsive maneuver. Again, powered descent initiation is about a 10 or 11-minute burn that will slow the spacecraft's descent. A lot's going to happen after that 10 minutes, Josh. This is a single continuous burn. After that, we're going to see a lot of events in rapid succession: pitch over, vertical, and terminal descent.
And we just heard another call out from the prop console saying that feed line prep is complete. What that means is Nova-C's propulsion system, that mixture of liquid methane and liquid oxygen, that feed line is prepped, getting ready to go into an injector to blend those two propellants, and the propellant and the oxidizer, and have ignition of PDI. We're tracking that in just under a minute, Gary.
Converging on burn attitude.
Lander is getting into the correct attitude required.
Feed line prep complete, both sides.
Another call for feed line prep complete for liquid methane and liquid oxygen in preparation for this PDI burn.
"15 seconds, exec mode."
15 seconds to exec mode. We're tracking a little less than a minute, though, until the time of ignition for powered descent initiation.
Settling. Ignition. Throttling up. Main stage.
There we heard main stage ignition. That's coming from our prop console, Rob
Good
Moorhead.
control.
GNC call on good control.
Thrust await 1.5.
These are great call-outs in between our prop console and our flight manager, Scott Tamblin, calling it as the data is feeding into the lander, which means we are continuing to have good communications. The lander is sending that back to flight controllers in Nova Control. Gary, something we prepared for, we planned on, is that loss of communications, and that's why we have this.
I see good thrust control.
It's a good thrust control call from prop, but that's why we have this autonomous lunar lander. You know, we program, we know that, hey, we want to light PDI in this moment. These are the steps you need to get there. But from here in, this is an autonomous lunar lander, and flight controllers are monitoring communications and tracking the progress right along with the public right now with us.
Nova C has the helm. It is in control and is making the decisions necessary to ensure a soft landing. We heard call-outs about thrust, full thrust right now. There is the ability to throttle that thrust, and we'll see that throughout the descent as the fuel tanks continue to unload and we expel that propellant.
And we did have a few questions come in about how much gas are we giving this to slow down the vehicle. And we want to remind folks that this PDI burn goes
Commanded thrust 90%.
Goes in just about 90% right on time. So it goes in at 90% in order to, if the lander makes a decision and says, I need to slow down more and make a decision to make a safe landing, it's able to add a little bit more oomph and make that decision a reality rather than just a possibility.
Fido, I'm showing 500 kilometers to target, but my display's a little bit stale.
That's the mission director, Tim Crane, calling about 500 kilometers, but stating that his information might be just a bit stale.
1,000 PSI in the helium tank.
It's part of the reason we're showing this animation, Josh. Of course, this is not telemetry driven. We're just showing you exactly what's happening. As we hear the calls, this information is relayed through the audio loops. Not enough bandwidth to do a live stream of this, so we're relying on the data that's being fed from Nova C to Nova Control.
Yeah, that data is going into the flight controllers, and what you're seeing on your screen right now is just to give you an idea of the vehicle's attitude. You heard them talking about moving to a burn attitude. This is what we expect Nova C is doing right now. It is a simulation in the large screen just to give you an idea of what's happening over these critical approximate 10, 11 minutes of PDI-powered descent initiation, trying to slow Nova C down, bring that acceleration down to about 1,800 meters per second. And there's some follow-on steps after that, Gary. It involves pitching over the lander using that gimbaled engine. We heard the maneuver to burn attitude followed by main engine gimbal checkout. So they'll use that gimbal to pitch the lander over and start a vertical descent. This is where we start getting a little tricky as far as there is a final approach. It may add a few seconds, it may add a little bit of time, but we are intended to land right around 17:24. That's 5:24 p.m. Central Time. But know that there is some give and take. We're also expecting, plan for, and train for a little bit of loss of communication during this process.
That's right. And that communication is absolutely important. And part of the reason, and we've been stressing this, Josh, is the autonomous operations of Nova C. Part of that is after it performs that pitch over maneuver.
400 seconds to go on braking 1. Good control.
Fido, I see TRN depause processing in flight.
All right, that was the call that we were waiting for. That was our major problem we've been working on in this dynamic situation, is getting those images processed from the HRN camera, TRN camera, which in this case, a dynamic situation, we had to improvise a little bit and reach into those 2 laser beams from NDL, figure out a patch while we were in lunar orbit, just about 2 hours, and it sounds like we are getting good readings from those images. Absolutely remarkable feat. We also happened here, I think it was 400 seconds remaining. That was coming from Fido and Flight Dynamics. Sean Stewart working the console this evening.
This is excellent calls to hear. Hazard relative navigation is going to be used after the pitch over maneuver. This allows Nova C to make some decisions and scan the landing site underneath it and make decisions in an area that calculates the terrain to make sure that it's landing in a safe landing zone.
Right, so we finish up PDI, pitch over, and we have to use that hazard relative navigation, a critical tool in order to land on the moon, to make those decisions, right? There's no human eyes, human elements deciding, okay, I see the hazard, I need to steer this way, or maybe press the gas, press the brakes. This all happens autonomously, and this is a huge requirement and a great call out to hear about the HRN camera system and processing those images. Right now, I am tracking 5:16 p.m. We expect PDI to go until about 5:21, 5:22.
300 seconds and breaking one.
Or about 300 seconds to approximate those numbers.
Very precise. Josh, after those final series...
Thrust to weight is 1.7.
Following along, after those critical maneuvers...
Committed thrust still 90%.
90% thrust. We'll hear those call-outs periodically. We started at full thrust, 90%, still throttling.
Nominal.
And good performance on that engine.
That's a great call out. Two things there. Nominal performance on this engine as well as the helium tank. So what we haven't mentioned so far in the show is that the helium tank pressurizes that liquid methane and liquid oxygen tank. But in addition, it's also used for reaction control system. Those are the small spurts that you see at the top of the lander in the animation that control the vehicle's attitude. So for things like landing on the moon, you really want to land at the right attitude. That way your antennas are facing back, direct line of sight to Earth, and you can get that ultimate confirmation once you do suspect that you have landed on the moon.
The antenna alignment is an important element of landing on the moon, Josh. We're expecting the high-gain antennas to be pointed towards Earth to confirm, but there may be a delay.
We are expecting some sort of delay. I had talking to the mission directors about how quickly we could receive a positive confirmation after this landing process is through, and there was some dispute over how long. The earliest was just about 15 seconds after we see timing of when the event is supposed to happen. So right now we're tracking about 5:24 p.m. Central Standard Time. So maybe anywhere from 15 seconds after that, maybe a few minutes, 2 to 3 minutes while we work to acquire that signal. Because as you mentioned, the lander is going to a general area.
9 kilometers altitude.
9 kilometers altitude call from Tim Crane. The lander is going into a general area that we say, this is the general area we want you to fly to. It's using that hazard relative navigation to make better decisions about this is an area with the least amount of slope. This is an area that's free of boulders and other obstacles. So it's making autonomous decisions about where to go.
3 minutes to go, breaking one.
3 minutes call. Just to wrap that up, when the lander is making those decisions, Gary, it's also very difficult to track. We've been very fortunate thus far tracking communications to this point.
To wrap that up, Josh, 3 minutes, that brings us to just shy of 5:22 p.m. Central Time. We should hear that the power descent and initiation burn is complete. Then we'll begin the next series of maneuvers to get us towards vertical and terminal descent. It starts with the pitch over.
And just looking at our notes here, we did go into this burn expecting pitch over at 5:21 and 57 seconds. So good call out on the timing of that maneuver. It's important to remember PDI starts an engine burn that does not stop until landing. So this is a throttleable liquid methane, liquid oxygen engine. We lit the engine at PDI, and while we are changing into a pitch over, vertical descent, and terminal descent and then landing, that is a throttle down to the lunar surface. And when we do get out of PDI, if we hear that call of PDI complete, good burn, everything after that is going to happen in very quick succession, Gary. The time it takes to go from pitch over to landing, or what we estimate landing to be, just looking at maybe 90 seconds is what we expect nominally.
3 minutes to touchdown.
There is some wiggle room. 3 minutes to touchdown call from the mission director.
For an on-time landing, that sets us a little after 5:23 p.m. Central Time.
Right, our notes going into this burn, 5:23 and 25 seconds.
The autonomous operations, Josh, sets this to a clock. This is exactly what we got relayed before the start of our
Still
coverage
processing.
today. We're right on track.
DPAS, terrain relative navigation measurements.
Excellent call out. That solution that flight controllers were working so hard on to make sure HRN was working, pulling on extra resources that weren't originally planned for from those 2 laser beams from NDL. It appears and sounds like that solution is working, and the people working to patch that software were certainly under pressure. The clock was ticking as we went into that extra lunar orbit. It wasn't a situation where we could just sit in lunar orbit and try to solve our problems indefinitely, and it's sounding good so far on the call outs.
2 minutes remaining till touchdown.
2 minutes to touchdown. That required a patch to be designed on the ground and uplinked to Nova C to confirm that those laser sensors on NASA's navigation Doppler lidar could be routed to the terrain relative navigation and hazard relative navigation. That call out is fantastic.
Fighter, do you have an altitude reading?
Standing by to see if we can get an altitude reading from FIDO here. That's Flight Dynamics Officer Sean Stewart on Blue Team.
Confirm, that looked like a pitch over gimbal. Let's do it.
Sounds like we have some data that confirms pitch over. This starts the HDA process. That's hazard detection avoidance. Throughout this show, you've heard Gary and I talking about the problem that was attempted to be solved in lunar orbit, making the decision to not only postpone this show.
NDL indicates altitude of 1,000 meters.
1,000 meters call out from NDL. That is coming from flight management. This is a system right now. NDL was not intended to be the primary landing system on this. Instead, we're using 2 laser beams from NDL and feeding that into that hazard detection and avoidance system that you see on your screen right now, with the lander making autonomous decisions about where it wants to land. That is generally
less than 1 minute remaining to touchdown.
Less than 1 minute remaining for touchdown.
And again, that's the time of touchdown. It may take some time to actually confirm the status of the lander.
And in this process, we do have a deployment of Eagle Cam attempting to take the third-person images of Nova C going down to the lunar surface. We are inside of 1 minute, Gary.
Yes, we're well into blowdown.
And we're tracking here in the broadcast booth. The clock has reached the expected.
May take a minute for comms to reestablish. Stand by.
There it is, mission director beating us to it. We've reached the expected time of landing, but now is the process of waiting for comms, and we are in standby mode, as you heard it from the mission director, Dr. Tim Crane. And 1 minute has elapsed from the notes that we have, Gary, of that original burn starting at PDI.
And you have carrier lock.
That's MD asking if we are getting the ground stations locked on to Nova C. That carrier lock call, Gary, we expect that to come from GroundNet or COM. That conversation possibly not happening on our public channel that we have access to. We're just standing by to hear that come through the channels as we approach almost 2 minutes since we estimated the landing time. We did get a few call outs on the side, folks coming into the room saying there was about a 2 minute forgiveness in our timetables.
We are checking our antenna reception.
Checking antenna reception. And we're standing by, Gary. We're standing by just as we approach 5:26 p.m. Central Standard Time. Given those mission directors' notes of the flexibility between what we were tracking, what we were given was just about 5:24.
All stations, this is MD. Please look back through your logs and confirm the last information you had, and we'll determine this is a comm outage.
And that's the mission director, Gary. These are our notes here of what we believed. We talked about the comm outages with the lander making autonomous decisions. This is the process of going through the last bit of data that came into Nova Control and working to verify, okay, this is the last bit of data. Where was the lander possibly going? How do we look for it and establish those communications? Nova C uses 4 antennas placed at the top of the lander that are designed to capture these communications. But we did expect this. We talked about it, that this is a communications challenge in it of itself, and right now we're standing by to hear that communications call out.
We're just a little more than 3 minutes from the time of when the clock reads 0 for Nova C landing on the moon.
And we just checked with our team here in the broadcast booth, decided to let's stay on this. All the chatter we are not hearing on this public channel, Gary, all things indicate that we are working to solve a possible communications challenge in this moment. So we're going to continue to stand by.
For those following along.
MD Prime on IM1.
Go for Prime.
Yeah, I guess you polled the room looking for states, and we're going to go ahead and cycle the ground transmitter on Goonhilly and do some RF sweeps. Is that your plan?
That's correct.
Roger, copy.
And that's just what we had in mind in our notes, Gary, is that if we encounter a communications challenge, we mentioned how difficult it is to land on the moon and continually have those communications. What you just heard there is folks talking about using the Goonhilly Earth Station Limited dish in the UK to do a sweep looking for that signal. We mentioned that autonomous process of the lander reassigning itself somewhere that it believes is safe. Going into it, we heard that the HRN camera was functioning and able to make those decisions after what was a 2-hour orbit of problem solving with Intuitive Machines' TRN and HRN cameras, the laser rangefinders assigned to those. Those are the ones that Intuitive Machines installed inside the navigation pods. The laser rangefinders were not activated. We went to NASA and asked to use 2 of the laser beams on the navigation Doppler LiDAR.
That's right.
And spent 2 hours in orbit.
Team, we're going to confirm our pointing vector with our antenna for post-landing.
Yep. We spent about 2 hours in orbit to solve that problem. We got good readings on the way down. And right now, we are working to confirm communications on the surface of the moon, roughly around the Malapert A region. That is the South Pole region of the moon.
That's right. What we do know is the powered descent initiation. We were following along in the status calls. We executed a pitch-over maneuver, and we're counting down the clock to a landing time of 5:23 p.m. Central Time. Well, Josh described those processes of working on the communications component to confirm data from the lander, pulsing the teams surrounding him to check the status of Nova C and the data that they were receiving here in Nova Control to confirm landing. And part of that, Josh, as you described, is communications. We're standing by.
Fido MD on IM1.
QMD.
I'm looking at our phase plane there for the last part of the flight. Looks like we had excellent pitch and yaw control throughout, but I did see a little bit of a roll excursion. Could it be that we landed off angle and roll in the final phase?
So I do see we had up to an 8-degree excursion. We're about to begin the roll maneuver, which is about
terminal phase.
The terminal phase, which is a large roll maneuver to get to landing attitude. That's the last data point I have. But up until that point, we were really solid.
Right, so terminal phase begins at 30 meters? Or post-HDA?
Post-HDA.
Post-HDA.
400 meters.
Very good.
And that's a great conversation confirming.
That's good ground network, good for box scan. Make that go.
Yeah, that was good confirmation of the process that we were very familiar with, talking about the attitude of the lander, making sure that those antennas are within direct line of sight with Earth stations, ground stations on Earth, excuse me.
Mission director at all stations, we're also updating our pointing vector with our dishes to make sure that they're tuned in on our final landing site.
There's a caller searching for that communications back to the ground station. This one particularly is in the UK that's tracking us. And it's important to note, Gary, that we have an entire network dedicated to working these communications problems. It's been active this entire mission. And the largest, most powerful dish out of all of them is about a 64-meter dish in Australia. That time to search with that opportunity with the largest, most powerful dish, we're looking at about 12 to 13 hours after our estimated touchdown. So this is a process that we could be looking and searching for the lander's signal for confirmation for quite some time, but we're going to continue to listen in and stand by as our flight controllers are working with the ground station in the United Kingdom to work this issue, work this problem. It's another challenge, very similarly to the challenge solved just to make it this far.
Science of life, we have a return signal we're tracking. We have an onboard fault detection system for our communications that after 15 minutes with lack of communication will power cycle the radios, and then after that for another 15 minutes it will then switch antenna pairs. So we have some time here to evaluate. We do have signal that we're tracking, so we'll see what happens.
There's a great call out about the autonomous systems installed on our Nova C-class lunar lander named Odysseus. The process he's mentioning, Gary, is very similar to the one that we were preparing ourselves for at AOS, to where the lander has systems in place to recycle its antennas, to switch antenna pairs, and that was very similar to what we thought we were going to need to do after acquisition of signal. When we separated from the second stage of the launch vehicle, if we made it to a certain point, the lander was autonomously programmed to start taking matters into its own hands, and that was the information that our mission director, Dr.
We're not dead yet.
We're also not dead yet.
And the key here, Josh, is patience. It's 5:34 p.m. Mission Director Tim Crane confirming that it could take 2 phases of 15-minute increments to confirm the status of the landing. So we could be here, and we'll stand by and monitor as Nova Controls continues to work this issue.
Yeah, tense moments inside of mission control with the most qualified folks.
We're picking up a signal from our high-gain antenna and transmitter. It's faint, but it's there. So stand by, folks. We'll see what's happening here.
All right, we're going to continue to stand by. Let's keep this camera on inside of Nova Control. It sounds like we are getting some kind of faint signal.
I want to send a series of commands to reactivate, make sure we're transmitting to keep Equasonics active.
We're still standing by. The last call from Mission Director Dr. Tim Crane was that we were getting a faint signal from Odysseus's high-gain antenna.
All stations, this is Mission Director on IM-1. We're evaluating how we can refine that signal and dial in the pointing for our dishes. What we can confirm, without a doubt, is our equipment is on the surface of the moon, and we are transmitting. So, congratulations, IM team. We'll see how much more we can get from that.
An excellent call from our Mission Director, Dr. Tim Crane.
IM-1.
And over to our
Prime.
CEO, Steve Artemis.
Yeah, if I could just pass on a few words to the entire team in Intuitive Machines at Superbab and here in the Mission Control. What an outstanding effort. I know this was a nail biter, but we are on the surface and we are transmitting. And welcome to the moon.
Houston, Odysseus has found his new home.
An excellent call, and this is our team of Intuitive Machines mechanics and their families, their friends, everyone who has sacrificed so much to make it this far.
Stations.
How about that call, Gary? That was something else, a faint signal. Now it's time to work on refining that signal. But Dr. Tim Crane, our mission director today, making the call. Odysseus has a new home.
It shows the disciplines of the flight controllers in Nova Control. They waited until there was absolute confirmation that there was a signal, and then that was when they took the moment to celebrate. We saw that it wasn't just the individuals in Nova Control that contributed to the mission. The contributions to enable the success of Nova C's landing on the moon stretches far and wide. We showed, of course, some of the folks watching there, but really it extends even farther than this. A wonderful and truly amazing moment to celebrate. The U.S. has landed on the moon once again.
And to everyone, you mentioned it goes beyond just the folks that we saw on camera waiting and working through those tense moments, but their friends, their families, and everything it took to get to this point. We're still expecting an image. We expect that to come down sometime in the future, especially as we look towards some high-resolution images. Let's go ahead and it sounds like we do have a message we'd like to cut to. Can we have that message special for our folks, our employees, and folks watching at home?
Hey, that's right. With Nova C landing at Malapert A, congratulations, like you said, Josh, are flooding into the teams that made this happen. Really sets a tone for the American leadership and the future of a strong lunar economy. So here's NASA Administrator Bill Nelson.
On the 8th day of a 250,000-mile voyage, a voyage along the Great Cosmic Bridge from the launch pad at the Kennedy Space Center to the target of the south pole of the moon, a commercial lander named Odysseus, powered by a company called Intuitive Machines, launched upon a SpaceX rocket carrying a bounty of NASA scientific instruments and bearing the dream of a new adventure in science, innovation, and American leadership in space. Well, all of that aced the landing of a lifetime. Today, for the first time in more than a half century, the U.S. has returned to the moon. Today, for the first time in the history of humanity, a commercial company, an American company, launched and led the voyage up there. And today is a day that shows the power and promise of NASA's commercial partnerships. Congratulations to everyone involved in this great and daring quest at Intuitive Machines, SpaceX, and right here at NASA. What a triumph! Odysseus has taken the moon. This feat is a giant leap forward for all of humanity. Stay tuned.
All right, thank you, Administrator Nelson. Again, Nova C and the United States has landed on the moon at 5:23 p.m. Central Time today, February 22nd, 2024. Congratulations to Intuitive Machines on the successful landing. Science and data gathering is already underway and will continue for roughly 7 days on the lunar surface, activating payloads and gathering important scientific data to help ensure future successes in Artemis missions. For more about NASA's CLPS initiative, visit nasa.gov/CLPS.
Gary, it's been quite a journey for all of us at Intuitive Machines. Thanks to NASA for the continued support to enable today's successful landing, and of course, everyone at Intuitive Machines, their friends and family who made all of this possible. That will wrap up our coverage of Intuitive Machines' IM-1 mission. Thanks for joining us.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
3, 2, 1, 0. All engine running.
Let's go.